All right. Oh, thank you, thank you. Good morning, everyone. Welcome. Oh, I didn't. Excuse me. Can I have a clicker? Sorry. Can I have a clicker for the slides? Clicker. Thank you. Sorry about that. There we go. Thank you to everybody who attended yesterday. Thank you also to new faces who might be here today. If you weren't here yesterday, please join the conference Slack. There is a QR code on screen. I'm going to do a little bit of a recapitulation of the start of my talk yesterday. On the conference Slack, you can get up-to-the-minute updates about changes to the conference agenda, get in touch with the organizers if you have questions. To that effect, let's meet the organizers. Hi, I'm Blaine. I have a background in autonomous vehicles and formal verification of highly concurrent programs. Right now, I do some combination of AI safety field building and consulting in Tokyo. I will be on stage most of the day, emceeing, bringing people on and off. So if you have actual questions, you should talk to Caitlin. Caitlin is not in the room right now. Caitlin is just coming in. On the back left. Anyway, this is Caitlin. Caitlin has been a valuable asset in making the conference run smoothly. If you have any questions or concerns, please get in touch with Caitlin, and she'll either be able to sort your problem then and there or find you someone who can sort it. Since I have a little bit more time today, I'm going to take the liberty of running you through a history of AI safety in Tokyo specifically. And then I'll give you a map of the institutions that exist in Japan, how they relate to each other, and how you can get involved with each. So cast your minds back to November of 2022. More than a year ago now, ChatGPT was released, which changed public perception around AI in a big way. From the inside, ChatGPT was not a huge step forward. If you had been following the language modeling literature, you would have seen things smoothly transition from GPT, GPT-2, GPT-3, GPT 3.5. Similarly, there was great progress in other fields of machine learning, computer vision, natural language processing, et cetera, et cetera. But ChatGPT was really a tentpole moment in bringing public attention on AI and showing how much we'd progressed since 2010. Not uncoincidentally, a couple of months later, I founded AI Safety Tokyo in January of 2023 with the aim of building a safety community in Tokyo, bringing people with interest in safety up to speed with what the latest research was so that they could maybe transition into doing safety full-time. Trying to connect people interested in safety with other people interested in safety to build something. Back in November, parallel to the release of ChatGPT, a company called Conjecture, based in London, was investigating Tokyo as a hub for safety in East Asia. The current safety hubs are in San Francisco, London. They were looking to do something in the Far East, and they were connecting with people in Tokyo to try to bring people together and start interest and alignment in a very similar fashion to what AI Safety Tokyo was trying to do. To that end, in collaboration with Araya, Kanai is sitting in the audience, they organized the Japan Alignment Conference in March of 2023, which brought together researchers from various companies and institutions to discuss alignment, the alignment problem, how seriously we should take existential risk from artificial intelligence, and the kind of work that might go into solving it that would be appealing to people working in Japanese AI research fields. A few months later, A-Life 2023. A-Life is a large field of research in Japan that is some combination of robotics, artificial intelligence, and biology. The Inhuman Values and Artificial Agency Conference was organized by Simon McGregor and a couple of his colleagues. Notably, Manuel was involved. And that was aiming to bring A-Life researchers in contact with Agent Foundation researchers. Because when you look at, rather than the setting, the actual practice of doing research in both of those fields, there's a surprising amount of overlap. A couple of months after that, going back to the kind of global view, there was the AI Safety Summit organized in the UK, which brought together representatives from G7 nations and large AI companies to discuss how we might take a regulatory approach to addressing risk from artificial intelligence, both existential and regular. And in the wake of the AI Safety Summit in December, January of 2023-24, the Japan AI Safety Institute was founded. The Japan AI Safety Institute currently has weak ties to AI Alignment Network and AI Safety Tokyo, and we're hoping to strengthen those over the coming year. Fast forwarding to this year, in January, the Japan AI Alignment Symposium was conducted by a research organization called Mitsubachi. Mitsubachi is a cross-disciplinary, cross-organization research collaboration organization in Japan, focused on bringing researchers who have similar interests together across institutions, countries, and domains. A lot of research in Japan happens siloed within a particular team or institution, and they're trying to foster more collaboration. To that end, they noticed that AI safety was an important topic and tried to bring people together to discuss safety, again in collaboration with Andrei and the Japan Alignment Network. And then, in April of 2024, today, Technical AI Safety 2024 occurred in Tokyo, with the aim of bringing, with one of its aims being to bring the Japanese research community in contact with the international technical AI safety research community. Here's a little map of existing institutions. It looks a little scattered and difficult to read. That is intentional because the AI safety community in Japan is a little scattered and difficult to read. The bold links represent shared staff or a deep connection. The AI Alignment Network shares staff with the AI Industry Foundation. The AI Industry Foundation shares some staff with AI Safety Tokyo. The dashed lines represent weak ties or collaborations on events. Notably is this weak link from the AI Alignment Network to the Japan AI Safety Institute via the Matsuo Lab at University Tokyo. Yamakawa Sensei, who is one of the founding members of the AI Alignment Network, is a researcher at Matsuo Group. And GPAI, the Global Partnership on AI, which is not itself a Japanese organization, but happens at the minute to be co-directed by two Japanese people, is trying to connect the Matsuo Lab with the Japan AI Safety Institute to organize a project on safe AI in Japan. So I'm hoping that over the next couple of years, we can turn this scattershot and difficult to read diagram into something that is more legible and easy to interact with. But as it stands, if you are a researcher currently looking to focus on safety, if only you had connections and funding, probably the AI Alignment Network is the best place to reach out. If you are working in industry and you would prefer that your colleagues had saner opinions about AI and its future, you should reach out to the AI Industry Foundation. If you are personally interested in AI safety, but not currently professionally interested, maybe reach out to AI Safety Tokyo, start joining some of our weekly seminars, get up to speed on the topic, and then consider making a career change. So that's it from me this morning. I would like to hand over now to our first talk of the day, Mr. Andrei Krutikov from Noeon Research, who will tell you about Noeon's approach to safety.
Andrei. I'm CEO of Noeon Research. Noeon Research is an R&D company that is trying to find an unconventional approaches to an AGI. Notable features of our approach are representing goals and purposes as first-class citizen objects, and also representing knowledge in discrete manner. But what is knowledge? So we tend to say that knowledge is anything that agent decision-making procedure can condition of. It is broad definition, so let me focus on types of knowledge. So what types of knowledge exist? We divide the knowledge in two categories: factual knowledge, or know-what knowledge, and procedural knowledge, or know-how knowledge. One might think of latter as of capabilities. Now let me talk about our operational definition of interpretability. We consider a system to be an interpretable one if operator can exactly locate where knowledge that is influencing observable behavior is stored, and second, operator can change system's knowledge in a manner that is predictably changing the behavior of the system. Of course, the second one can be only done by using some tools, and it will require some operator training. Interpretability, of course, is important for AI because, well, interpretability allows us to assess capabilities of the systems so we can control them. Also, if we want to perform some manual intervention, we also need to know where to perform this intervention. This all is needed to establish trust to the systems that we build. So now let me talk about existing solutions that are there. So of course, there is a symbolic good old-fashioned AI. And in good old-fashioned AI, we store factual knowledge and procedural knowledge separately. Factual knowledge being stored in knowledge graphs or knowledge databases, while procedural knowledge is external solvers, external kind of reasoning engines. Is it representable? Well, yes. Sorry, is it interpretable? Yes, because one might locate inside the knowledge graph the precise location where, let's say, relation triplet is located. Is it corrigible, though? Well, modular the external procedures. One, of course, might change something inside the knowledge base, but it's difficult to change algorithms. Now, large language models store both factual and procedural knowledge in the shared space, in the shared weight space. Are those interpretable? Well, with clever tricks, yes. Is it corrigible? Prohibitively expensive. The retraining cost is high. Now, our solution, akin to LLMs, store factual and procedural knowledge in the same semantic space. However, this space is represented via discrete structures rather than weights. So it is way more legible. And I dare to say that it is both interpretable and corrigible. We are building a system that is interpretable by design. In addition to discrete representations, we develop inspection tools that we consider as an essential part of the whole system. Those tools help us interpreting systems in hierarchical manner on several levels of abstraction, or as we call them, language levels. So language level 0 is the fundamental level at which all our stuff is stored in discrete structures, namely in partially ordered sets, or also known as directed acyclic graphs. They are enriched with some structure, like maybe embeddings or labels or user data. And information retrieval from those structures is done via what's called subgraph isomorphism matching problem. And if one wants to put new information inside this graph, one has to perform a graph transformation. Also, any reasoning that is happening inside our system is also done via graph transformations. That's the screenshot from our internal tool. This is the tool we use for something we call surgery. We perform this surgery on graphs, so we have very detailed view on what's going on inside. On the left side, you might see the smaller pattern that is recognized in a big graph. Then language level 1 is the level at which we talk about executables and execution trajectories. At this level, we store procedural knowledge in explicit form, and this is the level where we get our transparency over inner workings of any reasoning process that is going in our system. Again, this is a screenshot of the tool that we use to deal with the language level 1. You see there's a bunch of rectangles representing calculations, and they are patched together with control flow links and data dependency links. Now, one might ask, well, where is the factual knowledge inside the language level 1? The answer to that is this. We consider a factual statement to be a statement insofar as this statement is about computation results. So, in other words, when we talk about something happening in outside world, we're talking about this in terms of some process in outside world, some computational process in outside world, ended with certain result. So, it is natural for us to represent facts as short sequences of trajectories. Now, language level 2 is the level at which we have ontologies, models, goals, agency in explicit form. This is also the level at which we deal with operator input. This is the level at which we elaborate operator input. Also, this is the place where we identify the lack of required semantics that is needed to perform the user request or answer user's question. Again, this is a screenshot of one of our tools that we use. Here you can see the textual input, which is then parsed into entities, some of them grounded, some of them not. The very same input then represented as invocations, so language level 1, procedural kind of knowledge, and presented to the operator in this form. Now, do we have parts that are not interpretable? Well, of course. For instance, the subgraph matching that I mentioned before is an NP-complete problem, so we have to use some heuristics and some help from machine learning models that speed up this information retrieval. Also, the user input, to make it more to make it more user-friendly, we might also deal with natural language processing. But those models, they are small, compartmentalized, and trained separately. So we consider them to be safe. This design choice also reflects the fact that we are not entirely happy with big models, with machine learning. So what we believe is that it is possible to build systems that are safe by design. No need to be reactive to large language models. We might want to build new architecture from the scratch, and that's what we do. So I think it's important to say that inspection tools are essential part of the system, because we do not consider our system to be finished unless we have those inspection tools. And also, I believe that the most important things like goals and beliefs and conclusions and capabilities should be first-class citizen objects. This concludes my presentation, and I welcome your questions. Thank you.
Do we have any questions? Perhaps we'll start with one from me. How do you make sure that this remains interpretable as you scale up? Like, program induction methods can induce programs with like hundreds of thousands of invented predicates, and those invented predicates aren't necessarily themselves interpretable.
Right. So I think the key thing here is that we structure the knowledge in hierarchical way. So our tools actually allows us to choose arbitrarily abstract level of considering things. So if one wants to deal with very large objects, very large, I don't know, trajectories, very large bunch of conclusions and reasoning process, one might. But also without, like, one is retaining the ability to actually drill down and look for details on demand. So that's how we can be sure that any part of the system is still inspectable.
At the back in the middle.
Thank you for the talk. This is actually an interesting direction. At level 0, you mentioned that you're performing a subgraph isomorphism problem, which is known NP complete. This would seem pretty untractable for really large knowledge graphs. What are you doing to address that?
Right. So it is indeed an NP complete problem. So as I mentioned, we utilize some ML models that help us with this isomorphism problem. But it's not just that. Of course, in general sense, there is no free lunch theorem, so we cannot guarantee good times for any subgraph matching request. However, in our case, our graphs are not random. They have very specific regular structure. So because of those regularities, we might utilize them to fasten up our search. Also, there is one have to understand that this isomorphism problem is not purely an isomorphism problem because we already have some parts of the request or some parts of the request graph matched. Because whenever a person asks a question, inside this question there are already known parts to the person who is being asked. So those are our kind of pinpoints.
Do you have like a garden path problem though, where you find a subgraph of a subquery and then you have extra data come in and the subquery stops matching? You have to like redo it from the beginning again.
Yes, the subgraph matching process is interactive in a sense that if we notice that, okay, this is taking too much time to find an answer, we might interrupt this process and ask user for clarification.
All right, thank you very much.
At the right.
It's very interesting. How's it going? Any benchmarks? Any like how far along do you think you are? Are you gonna get us AGI next year? 5 years?
That's a good question. I think our immediate plans is to build proof of concept within this year. I would say we are still in the intense research phase. So I already showed you some screenshots. Those are real. Those are from our tools. So I would say at this moment we are almost done with the knowledge representation part, and right now we are looking into external reasoning procedures.
Maybe 2 more. Koen, down at the front.
Thanks. So, can you talk, how does knowledge get into the system?
Right. So this is a really good question because in good old-fashioned AI we know that there was a problem with initial population of the knowledge bases. So in our case, there is no distinct kind of training stage and inference stage. The system trains and learns stuff online from the user input. So imagine if user asking system to do something, and within this request, user mentions something that system doesn't know. This will lead to the process that we call elaboration, and this elaboration process will ask user about the required semantics, so the required semantics will be extracted from the user. Of course, when I say extracted from the user, I don't mean that the system will ask everything from the user. It is also possible to feed in, let's say, a textbook on JavaScript or something like that, and the system will be able to kind of consume it. But basically, at the situation where we have a lack of semantics, we are requesting that from either user or environment.
One more. from Simeon down at the front.
That's a question for myself. Not the live stream, unfortunately, but so in transformer architectures and in ML, we've got a dictionary, and then we train the model, and we store the result in positional embeddings that in an arbitrary large space they set the words around that we just cannot imagine with our brains. So how do you solve that with the knowledge and ontology representation? What's the approach?
Right. So I think one of the metrics of how big or how capable the LLM is its size. In our case, the size doesn't tell you much because you might have a very, very big graph which is regular, like every node has the same degree, and in that case, this graph won't contain too much information. So what we can do, though, is to expand this graph with some kind of interesting topology, interesting geometry, and looking at that geometry, we can find a place where to store that information. So I wouldn't say that the limitations of the architecture, LLM's architectures, are applicable in this case.
Cool. All right. Well, thank you.
Thank you very much.
I'd like to invite, excuse me, I'd like to invite Manuel onto the stage to start our morning session.
All right, well, good morning, everyone. Welcome to Tokyo, I guess, if it's your first time here. I hope you enjoyed your time so far. Welcome also to, I guess, our online attendees. I mean, I'm sure that some of you are, awake pretty late or awake pretty early, so thank you again for attending. So I'm going to tell you, a few things today. I'm going to talk about something that Blaine already mentioned, so artificial life, and I'm going to give you like a 1 minute, 2 minutes intro of what I think about A-life. When people tell me about A-life as a field. Then I'm going to tell you about some of my research that has to do essentially with something that I think we could roughly identify as the problem of boundaries and the problem of agency. And then I'm going to try and tell you something about some of our recent work with Martin, the next speaker, and a couple of other collaborators, some of them being in Japan, some of them in Europe at the moment. So what do I mean by A-life? A-life is roughly the study of life as it could be. So we are interested in forms of life that don't necessarily abide by the rules of biology and life on Earth, but could be, say, I don't know, could be following different rules on different planets. So it could be astrobiology that we talk about. It could be life in simulations. It could be life on some machines. It could be, different forms of life that exist in a completely platonic world as far as we are concerned. So what we are actually looking at is different forms of life, different forms of, say, interesting systems that might even obey different types of physics. So we look at things that have to do with adaptation, autonomy, self-replication, self-organization, evolution, so on and so forth. Now, the interesting thing, is that in the last year or so, I've been engaging, I think, more actively with the AI safety and AI alignment community, and also throughout some of the, well, actually, thanks to some of the meetings that Blaine mentioned. The first one for me was actually the one that my company, Araya team over there organized last year. So that's where I met some of the people that are also here today, some other people that then gave me other opportunities to engage with this field. And I would like to focus on some of the areas that I believe are common between research that we do in artificial life and research that is happening within the AI safety and alignment, I guess, space. So some ideas, agency, boundaries, things that I mentioned already, could be open-ended evolution. I think there is an interest in AIs that can actually learn to evolve and can actually, self-improve, learn a way to self-improve that could lead, say, to problematic situations. We are also interested in things like, meta-learning, so you could just call it perhaps like in context learning, at least in some situations, adaptivity or adaptability, evolvability, so, second order functions, so like learning to evolve, learning to adapt, things like that. Today I will focus on boundaries, though. So the main difference that I would like to drive for now, and then probably bring back later during this presentation, is the fact that I believe there are two questions that are equally as important, but that nonetheless should be considered different questions. One question has to do with what an agent is, and the other question has to do with what an agent does. Now, clearly they are related, but the point is that if you want to tell me what an agent is, you cannot start by assuming that there is an agent. So you have to first tell me what some kind of entity, individual is, and then some entities will be agents, some other entities will not be agents. A chair, hopefully, is not an agent. Most of the people in front of me right now, I would go as far as to say everyone right in front of me is an agent. So I want to be able to say that some objects are not agents, some objects are. Now, this is often, I would say, probably not the case for some of the work that is happening in the AI safety space when people talk about agent foundations. There are exceptions. I'm mentioning Matt's work being some of the, a very good example of an exception. So people that are anyway studying what agents are, but in general, things are a bit different. Now, instead of, I guess, assuming that we have an agent, now there is there is also a surge in, interest in the AI safety space when people talk about boundaries as a key missing component. So here I'm particularly referring to this sequence of less wrong, but also to a smaller sub-community that is kind of growing. There was a workshop a couple of months ago in Berkeley. I'm going to be co-running another one next week on the mathematics of boundaries. So if you want, to go a bit further, what I mean by some of the differences here, there's also a difference in the kind of approach that people take when they ask one question or the other. Usually say for, if you want to ask what an agent is, you might want to start from something that has to do with a more physics-oriented framework. So we have dynamical systems, we have something maybe that has to do with information theory. But if you are ready to accept that you already are working with an agent, you might want to use something that is more oriented towards decision theory, some kind of utility theory, some kind of reinforcement learning. Now, what I will mention next is the, the sort of like big picture that I have in mind. So there are fields where agents is like the main thing. We kind of assume that agents are there. We don't really ask what they are. If we are doing sociology, if we are doing psychology, if we are doing economics, if we are doing to a certain extent computer science, we kind of assume that agents are a thing. We don't really question that. Now in some other fields, we don't really even bring out the idea of agent. So if we are doing some kind of physics, if we are doing some kind of geoscience related research, we don't really hear a lot about agents in those areas. And I would say A-Life is something that tries to be in the middle. We try to find like the minimal notion of agency that would make lower level, in some sense, interested, and higher level, at least like engage with our own definition. To this extent, I will now go into some of the work that I've done before, some of the other work that was in the title that I think well captures this distinction that I'm trying to drive through. So there is this idea, this framework called the free energy principle, originally coming from neuroscience, and that recently has taken off also in the alignment space. This is a proposal for what an agent should actually be. So the proposal is something like, well, if a system minimizes this particular cost function that we call free energy, that's an agent. The key part is something called Markov blankets that I will be talking about soon. We then have something very related to this, and usually these terms are used interchangeably, but I want to be clear that I believe they are quite different. There's something that is like the principle that I mentioned before, and then there's something that is called active inference that is also coming out in the alignment space more recently that has more to do with what agents do. So how do they make decisions? How do they come up with policies that actually achieve certain goals? This is a bit of a punch in the face, and I'm not going to go through all of the details. I'm just hoping that this will be useful to somebody if you ever have to go through these slides again. This is my sort of summary of what this free energy principle is supposed to be about. This is coming from 3 years ago, but as far as I can tell, the main arguments are still the same. My point here is just I will be talking about a specific thing, these Markov blankets, and then I will be saying, I guess, a few things about those and how I think we can actually move beyond them. So Markov blankets, so these are simple notions that come from the literature on graphical models. So here I have a simple example. I have a bunch of variables, a bunch of nodes. These are all random variables. Here I just want to say that x and y are conditionally independent given the variables in the middle. The variables in the middle are what people call a Markov blanket. If you are familiar with the separation criterion, well, here we are. There are other examples that I'm not going through in detail here, but I just want to drive the idea that there's something like, having a boundary, having some sort of like veil that separates something from something else. This is why people are kind of excited, I guess, about this idea. Now, in a paper that we published a couple of years ago now, we tried to make sure that, certain things were clarified, so we came up with a distinction. You might not perhaps like the names that we use, but again, I think there's a distinction that actually makes a difference. So there is something that we think is just the classical notion of Markov blankets, how I think Judea Per first called them in his book, 89. And then there's something that we think actually came out from this free energy principle literature. The former, I guess, has more to do with veils where we have random variables, but we don't really specify a notion of time. And then the free energy principle version tries to say something about stochastic processes, so time index random variables. And so now we have time series, and we want to understand conditional independence for variables in a time series. Now, there's some philosophical, take that usually people have with one or the other, but I guess that what I want to really go towards is the fact that for Per blankets, for the original notion of Markov blankets, there's no claim that they actually define the thing that actually is conditionally independent on some other thing. But this free energy principle is trying to tell us that no, the Markov blankets that they use, these Freestone blankets, actually tell us what an agent is. And we'll, is that really true? Well, we'll see. So this is why I'm mentioning, active inference on one side. We can do decision making. We can say we are doing inference with some Markov blankets, approximate method, amazing. But then there's also a thing that is like, no, we actually have a theory of what an agent is. And those are two very different claims in terms of strength, in terms of technical effort. So I'm going to be focusing on a couple of things. Again, I'm not really going through some of the philosophical side and some of the other stuff that is also interesting, but not particularly here. So the first thing that I'm trying to, bring out is the fact that if the notion of a veil, if the notion of a boundary is kind of well defined and easily understood without time being a variable, that is not necessarily true when you have time. So if we have a bunch of time series, like in this case, I just had 3, but there are various connections there, it's less clear exactly what is supposed to be independent of what. So is it an entire time series? Is it a node? So is it a particular say, node at a particular time? Is it like a bunch of nodes, like at different times? Like, it's not really clear what the entity is supposed to be here. Do we want a notion of agency that is time independent? Well, that's, you know, that's not trivial. Do we want a notion of agency that only exists at a particular time? Well, that may also not be what many people are interested in, because I think that most people identify as being themselves over time. Now, this is something that has been brought out by different people, including Martin, the next speaker. And, you know, I tried to summarize, again, another punch in the face. I'm not going to go through the details. The point is that I've seen at least 6 or 7 different ways that people have been talking about Markov blankets that are very different. They make different assumptions. Some of them work with time, some of them don't. Some of them assume that, you know, there are stationary distributions, some of them don't. Some of them include the past but not the future. Some others, there's a lot of stuff going on. So just labeling everything as a single entity, this Markov blankets thing, will not do the job. Now, another, I guess, well, possibly like the main issue, I would say, or the main potentially, or the main area, I guess, that might have something for us like to investigate, is the idea that, you know, if you want to have a theory of agency, a theory of something that tells you whether there's an agent that makes decisions, good or bad, you'd like to do that in a way that is, you know, as agnostic as possible. If you have to go into a system and tell me what the boundaries are yourself, then you're not really identifying an agent. You're just identifying your bias for that particular system. In some cases, this is a very good idea. Like if I build a robot, I think I have a very good notion of where the boundaries of the robot are, modulo some exceptions. But if I have some really complicated black box system, some LLM, how do I know that this system is not actually expanding on the internet, copying itself on some different system without me knowing, and I'm still looking at the same machine, thinking that there's an agent there, and this thing has moved on. This is not how, you know, this is not how we want to identify agents. We want to make as few assumptions as possible. And is this happening with this free energy principle? Well, kind of not happening. So we have some Bayesian network. So we then go and say, oh, we are interested in a particular variable or a particular set of variables. Notice that I'm not bringing out time again because time is complicated. So I'm trying to give you the general picture. If you add time, it's even more complicated. We identify some variable. We say this is the variable that we are interested in, and then we're trying to find the Markov blanket. Well, if that's the case, then, you know, is this really a theory of agency? I'm not sure. Like, if you had to select some variables of interest, it means you already had some notion, some bias towards those being important. And maybe that's fine, but then this is not a theory of agency. So there are then other issues, potentially, like, you know, there's a case that I didn't actually go through when you identify some Markov blankets. You have this case with a head-to-head, or also, you know, the case I think is called also the collider case, where you have two variables that are pointing to the same thing. If you select one of the top ones, one of the parents as being the variable of interest, the other one also must be part of the blanket. Now it's quite easy, and we did this like in this paper, to come up with cases where the other parent is evidently something that, you know, is carried out by a different system, something that you would like to call an agent. And I'm not sure that that actually needs to be part of a notion of a boundary or some agent. I don't want, like, you know, Blaine's leg kicking my knee being part of the boundary of me as an agent. All of this to say, there's a theory of agency, there's a theory that is just about some decision making. It's not just. There's a theory that is about some decision-making rule with different cost functions, different algorithms. The people are also interested in the AI safety space, this active inference stuff. That's fine. If it works, I'm very happy. I think all of my focus was on the other side, so the theory of agency stuff. Once again, like sort of a bigger picture, What an agent is, things like this free energy principle, maybe not. Some of the stuff that Martin will be presenting next, some of the work that me, Martin, and other people are doing, some of the boundaries work that is happening at the moment. And then there are, you know, theories of what agents do, reinforcement learning, some decision theory, framework, game theory, so on and so forth. With the last, I don't know, like 1 or 2 minutes, I will just try to go through like some very, you know, high-level story of some of the work that I'm doing with Martin, and then I'm hoping that it will actually cover some of the big holes that I'm going to inevitably have. So we are interested in agents. I think you got this by now. We are interested in agents of different kind. It could be in AI, but it could be also in other areas. So let's try and understand what it means for an agent to have some interaction with an environment, and let's use this notion of interaction to actually understand agent and environment themselves. So this is an idea to say, if you start by defining what an agent is, and then tell me that the environment is the complement, and then they somehow interact, well, that's great, but that may not be the entire story. There are very easy cases where I can show you that by starting with an interaction, I can get agent and environment, but I cannot necessarily go the other way around. So in this case, we just took like some idea where we are saying, well, let's take this blob and let's say that an agent and an environment are in a good interaction if they are inside, but not if they're outside. Well, there's this notion of internal model that comes from control theory, where we basically say, well, let me skip to the next slide because that's basically the point that I want to drive through anyway. There's this notion of bisimulation that is essentially some relation between two sets that preserve structure over time. So we want to try and represent some notion of interaction between an agent and an environment in terms of something that it could be a bisimulation or some generalization of, where we say, well, there's this particular relation, and this relation needs to preserve the interaction between agent and environment over time. What does that mean? Well, it means that we have some, that we are identifying agent and environment as dynamical systems that have some specific laws that preserve certain, interactions in a lawful way. So this also has to do, and this is the part that I will hopefully, where I can hopefully rely on Martin, giving us all a better intro. This has to do with something that is also related with the with Bayesian inference, with the idea of agents having a model of their environment, as in trying to understand the causes, trying to understand the states that are generating certain observations. And here, again, like a bit of a punch in the face, we can actually define some notion of consistency between agent and environment that probably has to do with biosimulations, but it's a bit unclear still. And this thing will actually turn out to be some form of Bayesian inference. And this is the part that I'm hoping Martin will actually cover. So to end, I guess, the talk, green, good stuff. Yellow, not sure. Blue, to do. Green stuff, so I think there should be more interaction between the A-Life field and the field of AI safety and alignment. I think some stuff is already happening, more could. Free energy principle for AI safety, not sure. Active inference for AI safety, possibly. We just have to, show it working. Other areas, I guess, that I'm interested in, so abstract notions of models, systems that actually model other systems, world models, so on and so forth. There's stuff that we are doing with Martin and other collaborators that I think will be relevant, but again, to see. Thank you.
You did. While I rescue my microphone, do we have any questions from the audience? Yes.
Thank you for the talk. You are saying that free energy principle for air safety, well, unclear status. Why?
Why
is it's not promising while active inference is marked as to
yes,
do?
so I would say my take is that the free energy principle is trying to be a theory of agency, and I don't think it is, because you are selecting stuff and then you're telling me, oh, this is the Markov blanket of the stuff I selected. But if you're selecting stuff, it means that there's something outside of this, say, theory or this principle that is allowing to make that choice. Like, this is the stuff that I'm interested in. And I would say that's outside the free energy principle. Then you can apply the free energy principle and you will get something interesting, perhaps. But what makes you say that this is the interesting bit to investigate? Active inference, you know, it's I'm a bit oversimplifying, but it's something like reinforcement learning with a different, you know, cost function, and maybe like different algorithms that implement like the optimization of this cost function, like some reward maximization like thing. And yeah, I think that's possible. Like, you know, in that case, there's no claim that that's a theory of agency. It's more like a theory of, yeah, an alternative to reinforcement learning. And I think that's a very, you know, worthwhile direction. Like, if it works, I'm very happy. Theory of agency, free energy principle, I'm skeptical. I don't see that being a theory of agency. I don't know if it helps.
Thank you. Can we move one row back?
Thank you for your presentation. So I've been working in active learning with Bayesian optimization for a few years, and I haven't thought about this theory, so the theory of agency. And I was wondering, this is a really simple question because I don't know a lot about this, but I don't really understand what will be the link with the theory of understanding the theory of agency and the AI safety. Is it some link that if we just understand that we have a thing or an agent somewhere, then we can just, we will be able to determine what is the problem and things like that? Or yes, so this is just my question.
Yeah, so I would say the systems that have agency are fundamentally different from systems that don't have agency. So let's say, it's not probably the best example, but if I build a robot and I implement like some algorithm for this robot to do stuff, things can still go wrong because it will be implemented it will be embedded. It will be in the real world, things can go wrong. But I would expect that a system that actually is an agent and can actually make decisions for itself, change its goals, be autonomous, will have a whole different class of things that could go wrong. So it could be like, you know, I think I mentioned a bit, you know, perhaps ambitiously some example earlier. Let's say that, you know, I have some LLM that is implemented on a machine right in front of me, like, you know, this is where I trained it. And now it's actually, you know, implemented and giving me inferences about stuff. And now I think that's an agent. Now, if it is an agent in the sense that I think it could be an agent, as far as I know, it could have replicated itself on a different machine somehow. Like, you know, it could have convinced a different person, oh, yeah, you should connect me to the internet and I should copy myself somewhere else. And I will still look at this machine thinking that the agent is there, when it could perhaps just be like some empty shell of something that has moved somewhere else. Yeah. So in some sense, I think we often assume that, yeah, the agent is there because that's where I see it, but then maybe it's not, or maybe it's just a shell of something that is somewhere else.
Yeah, so the problem is basically on the assumption we decide.
Yeah, yeah. I think it often works, but I think it doesn't always.
Yeah, that sounds to be a really complicated thing to do with minimal assumptions.
Yeah. But Martin is coming up next. Okay, a lot of pressure now, Martin.
Thank you so much.
Well, we have time for one more before Martin's talk. Perhaps from Shun at the front here. Keep your hand raised, please.
Thank you for wonderful talk. Autonomy is essential to AI life, but some of the AI life researchers argue AI alignment research try to suppress autonomy.
Yeah.
What do you think about this argument or contradiction?
Very, very good point. So I would say there's clearly an interest in autonomy in, say, AI life, and there's, as you say, an interest in autonomy in AI safety, and they seem to be like, different, probably like perspectives. We kind of want to understand what it is and maybe implement it, and then there's, the risk of actually having an autonomous system that could actually drive us to not want it. So I think the most agnostic position that I think we are taking is that we need to at least understand what autonomy is. And then whether you want to implement it, like on some crazy system or whatever, well, there should be regulations against that. And whether you don't want to implement it, well, at least you should know what not to implement in some sense. Like, if we have some, I guess, notion of autonomy that we kind of agree on, as in we implement this algorithm and the system will become autonomous, then there's decision making to be done there that is, I would say has to do more with policy making than with the research itself on autonomy. But I would say, yeah, we anyway need to investigate. I want to understand what autonomy is. And then I'm very happy to not have autonomous AIs, I think, yeah.
Thank you.
Okay. Thank you, Martin.
Thank you.
Sorry, Manuel. And I would like to welcome Martin.
Thank you. Yeah, hi. I'm Martin. I work at Cross Labs here in Japan. And I want to thank the organizers for inviting me and giving me a chance to talk about this research on when we can see a Moore machine as an agent. So there will be a brief motivation and then kind of the vibes of our approach maybe, and then I'll give the definition of this Bayesian agent interpretation, which is the kind of formal or technical part. And I'll make some comments and then summary. So one thing that would be nice to have, I think we will in the end agree, I hope, is a kind of general and formal characterization of when some open dynamical system, which is a system with inputs and outputs and some internal state, when such a system maintains or updates beliefs about a model of some other system, where this other system is the thing that causes the inputs to this open dynamical system. And additionally, when this system acts in order to achieve a goal in this modeled system. So this is kind of a very long-winded way to say when exactly this open dynamical system is an agent. Or, yeah, at least one kind of agent. So just to drive this home from another perspective, what we want is that whenever some open dynamical system is capable of somehow accumulating information about some modeled environment and actively pursuing some kind of goal in that modeled system, then this characterization should reveal that it's doing this. So my original interest in this question comes from my interest in formally understanding what living organisms are. So like Manuel said, I come also from A-Life, and this is like a fundamental question in A-Life. And I'm interested in this because I think life is actually very closely related to agency. But this is not what this conference is about. So, but I think you maybe have a similar interest in such a characterization, because if we had it, we would maybe be able to prove things like safety critical things about the beliefs and the knowledge of some system, and in particular the goals of this system. So what's our approach? I kind of call it vaguely a relational approach. And it kind of says, so this is very informal, but kind of a system is, or something is, even what it can be consistently interpreted as being. So if a system is some agent, then we say there must be some interpretation of that system as an agent which witnesses or reveals that it is an agent. And why do I call this relational? Because having an interpretation in terms of some model system or some goal, that's a relation to this model system or the goal. So that's why I call it relational. And why is this an advantage? I mean, I can't really prove this kind of statement, but it seems to me that like what being an agent is kind of like super mysterious. Okay, what does this mean? It is an agent. But if you have whether you have an interpretation as an agent, that's something I think we can kind of check, and it's like we can make this kind of formal characterization of this. Okay, so in our work we've up to now defined two kinds of interpretations. The first one, we call it a Bayesian reasoner interpretation, and this kind of says how when a system does some kind of Bayesian filtering on some hidden state of the model, of the causes of its inputs. And the second one is the one I'll talk about now, which is called the Bayesian agent interpretation. And this reveals when a system can be seen as solving a partially observable Markov decision problem. So it's actually, so that involves a goal, which is the maximization of the expected cumulative reward. Okay, so what is this thing? So first, let me say what a Moore machine is, because our definition only works for Moore machines, or, I mean, Moore machines are very general things, but this is what we make statements about. So a Moore machine has two functions. The first is called the machine update function. It takes an input and an internal state. So the internal states are called M here for machine states, and input is I. So it takes an input. It takes an input and a machine state and produces a new machine state. So in these kind of diagrams, the boxes are functions, and on the wires there's sets, and they go from left to right. The second part is the update function, output function, and this just takes an internal state and maps it to some output. Those two machines here, I'm going to assume they're deterministic. There will be some stochastic ones later. Okay, so next. Yeah, what the Bayesian agent interpretation does informally is kind of you guess, or first you need to guess an interpretation, which consists of this POMDP and a interpretation or belief map. And then you check if the beliefs that this belief map associates to the internal state of the Moore machine update according to Bayes' rule. That's why it's called a Bayesian agent interpretation. And then you check if the outputs of the machine are equal to the optimal actions for solving the POMDP. So maybe one thing I want to say is that yeah, this Moore machine we call the it's not really an agent, it's just a machine. Like, you don't know yet if it's an agent. We have kind of separated it from, we have kind of solved the Markov blanket thing that Manuel was talking about. We have a separate thing in itself. It's a mathematical object, not necessarily something in physical space. So we make this assumption that we know that we have this mathematical thing, and then like it could be a program, a software program, and each of these functions could be neural networks. Okay, so now how does this POMDP guessing an interpretation work? So a POMDP is is defined by some set H of hidden states. So those are kind of like the environment states, and the model. And this model is about what causes these inputs. And the model also is allowed to have a hidden state that is dynamical, so also produces new hidden. So the model basically takes a current hidden state and an output of the Moore machine, and then gives you a next hidden state and the input. And since it can be stochastic, it actually gives you a probability distribution over the next hidden state and input. So stochastic, this blue bar here, that just means that it's stochastic. And we also have a reward function, and that takes a hidden state and an observation to some reward, and that's the cumulative expected reward is going to be the thing that's going to be maximized. And the other thing is this interpretation map, which is kind of the main. I mean, we didn't invent this. I mean, this exists in the literature, but this is like a very important part of our approach. And this associates to each internal state of the machine probability distribution over hidden states. So probability distributions over hidden states are also kind of called probabilistic beliefs. So this is our notion of beliefs. And then if you have guessed this kind of interpretation, then you can check if your machine actually has this interpretation or is consistent with this interpretation. And how do you do that? Well, you have to check this, this equation, which looks maybe a bit scary, but if you squint a bit and you know some Bayesian, Bayesian updating well, then you can recognize that this is actually Bayesian updating. And down here is the string diagram version, which maybe helps you a bit more, I don't know. But let me go through this really quickly. So maybe up here you see this is the new state mu of I and m. This is the new state of the machine after receiving input and starting in state m. Mu of I and m is the new state. And this kind of is the parameter of the interpretation function or the input to the interpretation map, which gives you a probability distribution over the next states. And this probability over distribution over next state has to be this Bayesian posterior thing. So you can also see here, m is the current, is the internal state, and it has an associated belief over hidden states and also an output, and those are both fed into the model and then give you kind of a prediction of the next hidden state and input. And here, what this side shows is that if you predict the same input and get it and put it into this machine, then the new machine state, the belief associated to the new machine state after the update here is actually the same belief as is actually the same as the one you expected in a way. So this is kind of the way Bayesian updating works. And so you check this condition. This is all about having consistently updating beliefs. And the other condition you have to check is that your actions are actually optimal, or that the outputs of the machine are the optimal actions. So for this, you need to know the optimal actions for your POMDP, which is not easy at all, but let's assume we have them. And then you just check whether in each machine state, the output is the same as if you take this machine state, check what its belief distribution is, current belief about the hidden states is, and then check if under this belief the optimal action is the same as this output. Okay. So that was the tough part of the talk. And do you know how much time I have?
I think you have 3 or 4 minutes.
Okay. Tight. Okay. So the first thing to note about our definition is that it's independent of the environment completely. We only take the Moore machine and check if it has, and we guess these interpretations and we check if they are, if the machine is consistent with them. And we don't, for this, we don't have to put it into contact with the environment at all. Like, this is a pure property of the machine, which means that if you put this machine in contact with some environment, it will have this goal that we found out before. But this goal might not even be achievable in this environment, might not even exist. And so it might completely fail to achieve its goal or to do anything sensible in this environment you put it in contact with. So we say an agent is not something that achieves something. We say an agent is something that tries to achieve something. This is kind of the main difference to what Matt's perspective, which I think is kind of complementary and not less important, because he kind of says an agent is about what it achieves, and we kind of say it's about what it tries to achieve. And yeah, I think there will be some future perspective, and that relates these two things. What else do I want to say? Every Moore machine has trivial interpretations, so there can be only a single hypothesis or a single hidden state, and then and a constant reward function, and then all policies are optimal. There's also an interpretation that kind of makes it so that whatever the machine is doing, it's optimal. But yeah, those are not the only interpretations, and actually one machine has multiple, like it has these two, and then it can have many more. And they probably, I don't know, there should be a probably something, form a category. And we are investigating this. And the other important part is that it's only a sufficient condition for agency. So this exact Bayesian belief updating that we check with the consistency equation is actually too strong. It forces the machine to remember too much about the past, not only what it needs to remember in order to take the optimal action. So that's for the safety people, it's probably a bit disappointing. But we're working on doing this approximate version, which will hopefully allow us to have a necessary condition for a Moore machine to be an agent. Okay, there's also stochastic machines, but these ones are still pretty boring, the ones that are in this paper, because the interesting ones also need this approximation. So I think I have some more slides, but I think I'm going to stop here because it's just a kind of summary.
You have some more time if you'd like to.
Okay, let me just go through this quickly. So I described some steps towards formally characterizing when some open dynamical system maintains beliefs about a modeled system and acts in order to achieve a goal in this modeled system. And I think for the AI safety applications, we need a theory for arbitrary beliefs and belief updating mechanisms and arbitrary goals and problems. And we need the necessary and sufficient conditions for when a system pursues any of those goals. But we don't have this yet. We just have a sufficient condition for agents, and we only deal with probabilistic beliefs and exact Bayesian belief updating. For example, there's also things like possibilistic beliefs, and maybe there are many more kinds of beliefs. I wouldn't say that we are that we already know exactly how far these, like what really a belief is and what knowledge is. But that's all future research. Thank you. I'm happy to take any questions.
Do you have any questions from the audience? Can we start with Colin in the front at the middle? Runners? Colin Rowe, front middle.
Thanks, Martin. This is an embarrassing question as a question after the talk. It's really a clarifying question. So how does a Moore machine differ from other standard machine representations, and why do you prefer the Moore representation? What does it allow you to do that a...
Yeah, so there's, I mean, it's not a very strong condition, but okay, so why do we want this? So the important part about a Moore machine, there's one other famous kind of machine, which is called a Mealy machine. And actually, this is a Mealy machine. It produces kind of, so the inputs to the environment are basically the outputs of the environment. So this machine has one function, yeah, that turns the states and inputs to new states and outputs at once. The Moore machine has two functions. One that turns the input and the machine state to a new machine state, and one that produces the outputs. So why do we do this? Why do we like this better? Well, the main reason actually is, to be honest, that these Moore machines are the kind of things that solve POMDPs.
Okay.
I mean, it's actually, it's a subtle question in some way. We could talk about it, but it's, I would have to know what your background is. Give you
I'm not quite old enough to know Alan Turing, but I understand what Turing machines are, and I know finite automata. And so that would be the natural model that I would be thinking in terms of. So
Right. I mean, Moore machines are also, like, they're finite Moore machines are also finite automata. So there's no... And you can also, there's also a theorem that you can turn any Moore machine into a Mealy machine. But the thing is that, maybe one thing, the Moore machine kind of produces an output first, and then it gets an input and updates its state, and then it produces an output again. A Mealy machine is something that you cannot produce an output by itself. You always have to give it first an input. So the Mealy machine is kind of the thing that reacts, and the Moore machine is kind of the thing that can start some process, some interaction process.
And a null input doesn't change that?
A null input?
Yes.
So you
Giving the Mealy machine a null input doesn't...
If you give the Mealy machine a null input, it must have, if it has a, it must, in its input set, it must have a null input to deal with. So yeah, you can specify some kind of additional, like you can specify some state as the null input, so, but you will still have to give it to it in order for it to do its thing. It's kind of, by definition, you have to give the Mealy machine an input for it to produce an output. Okay. And like, if you don't give it its arguments, you can't apply the function, no. So that's why it's kind of, it's like, but this is like the mathematical precision that, I mean, that's why mathematicians, they are, I mean, like, let's say 5 years ago, I wouldn't have cared about this one bit, but it seems like maybe we have to.
Any other questions? Brandon, at the back in the middle.
Or maybe, like, for proofs. The thing is, in the end, for proofs, you have to care about these things. Like, you cannot prove things without making sure that everything is like the way you need it to be.
Thank you, thank you, Martin. Agent Foundations is kind of close to my heart. I'm over here. You brought this up, but there's clearly trivial examples of your definition of agency here. Like a thermostat, you could model it as one of these machines,
right?
But it doesn't fit the intuitive definition of an agent. And it seems like there's a broad class of things, like even autopilot on a 737 or something would fit, a model that might fit a model like this.
Why not? I mean, why does it not fit an intuitive notion of an agent?
I mean, we're not worrying about the safety of thermostats.
Right. That's true.
So,
but that doesn't mean that it's not an agent, no? I mean, well, at least in my opinion, it doesn't, because it's still trying to do something. like the thing it's going to try to achieve is perfectly fine. Like it's not going to kill us unless it's trying to make the temperature 300 degrees in this room, then maybe.
Sure. Then your thermostat is broken. But I mean, sure. Like we can have a very extremely broad definition of agency, but if you're worried about some of the more intractable problems in safety or something, it seems like it draws a pretty broad class of things, and we'd want to separate out agents from dangerous agents or potentially dangerous or some other class of things.
Right. I think, yeah. But I mean, like, I think you could use stronger definitions of agent, and I think like Matt's definition is more like also going in this direction. And I think we need to understand agency. We need to understand all of it. Like we can't just say, I just want to. I mean, like, I think it's not a good. I mean, I don't know. My intuition would be. I mean, I'm also interested in it from the biology part, but my intuition would be like if you only try to understand this one part of agency that's really where you already know it's important for safety, maybe you're gonna not actually understand the concept of agency, and then you're not gonna be able to prove the things you want to prove. So if you, let's say, if there really is this category of interpretations, then in this category, there should be like specific goals and like specific interpretations that are maybe dangerous. And they should have a property of something should make them dangerous. And then we should just formally say what that property is. But we also, like if you want to understand the dangerous agents, I think you also need to understand the non-dangerous agents to figure out what is the property that makes the dangerous ones dangerous. No? You need to, and hopefully formally. So, I mean, but this, I mean, I think you can have a different approach. I think it's fine. But like I'm kind of more envisioning this. You have this theory of agency, which is like general, and then like in this theory, you find this these specific parts that are relevant for safety, for example.
Okay, thank you. I mean, my intuition is that agency is not directly where the boundaries of the danger are or something more like this. I would care about what you brought up. Having a broken thermostat is a problem. And if we have a really intractable thermostat, we care about trying to fix that. So it's like, I think you're hitting on something interesting here, but it seems somewhat orthogonal to agency to me in a little bit.
I mean, yeah, I think there are people who use this word in maybe more like the way you mentioned. I think when people say agentic, I don't think that's really close to what I'm talking about, which also confuses me, but because I don't come from this background really. So, but I think, yeah, I think this, that's right, yeah.
All right, thank you very much.
Question from the live stream?
Yes, we've got a question from the live stream. Alisa asks, when you say that an agent tries to achieve its goals, what is a goal here? And I think I will add from myself. Does your conceptualization of agents as Moore machines allows you to offer some formal criteria for goals? Thank you.
Right, so here we use this, we use reward functions to formalize the maximization of expected cumulative discounted reward as goals, basically, so which are just given by, you choose a reward function and then you have a goal. And then there's this theorem about how all preferences can be represented by reward functions. So this is it's a very broad definition. I'm not really sure if that it really incorporates everything. But I think, yeah, so that's the idea. And so, yeah, maybe one more thing to say is that these goals, these reward functions, they are not, the way we formalize them, they don't have to be anywhere in the system. They exist as part of this interpretation, which is kind of a mathematical relation of the machine to this model system. So, or to the goal also. So yeah, like in some way, when this interpretation exists, maybe in some way it means that this goal is somewhere in the system, but this is the way it's in. The way it is inside the system is basically witnessed or revealed by the existence of this interpretation. So that's also the kind of categorical approach, that basically things don't contain anything. Things are completely specified by their relations to everything else. And that's the kind of...
So it's more of a manipulation of relations rather than numbers.
Exactly, that's why I say relational. I could have said categorical, but it's much more scary term, so...
Thank you.
We have time for one more from Ryota in the white in the middle.
Oh, hi, Martin.
Hi, Ryota.
Yeah, I was wondering whether you can always find some map to interpret like any machine as a Bayesian agent. It seems like you can always find something, and then maybe there's no correspondence with the actual environment, but it's always a model of something. So then, like, as long as you can first find some sort of Moore machine in a dynamical system, it always has some sort of model. Or can you find an example where you cannot find this interpretation map?
I mean, there's some examples, but yeah. So the thing is that these two they always exist, and the second one is not even completely trivial. Even though, so when there is a case, it's not very nice. So if the machine is stochastic and every state can transition to every state, for every input, there's a probability for the state to go to every other state, then it only has a trivial Bayesian interpretation, and therefore it only has a trivial agent interpretation. But I think the correct perspective to take is that it's not a problem that everything is a kind of agent in some trivial sense, because the interesting things are the powerful interpretations, like the ones where, I don't know, the goal is really like some abstract thing, or the goal is kind of, I could say, a dangerous thing, Yeah. Like, yeah, that's the idea. I mean, like, we don't really have very nice examples for this yet, and I think we need them, but that's kind of the intuition I have. That you need to look at all of them and the structure of them, because, I mean, yeah, hopefully they form a category, and there's like the most dangerous interpretation, or just the most, I don't know, the most compressed interpretation, maybe, with like the kind of final, the most particular goal or something. I think that's the hope.
Okay. Yeah. Thank you.
Okay. Thank you very much, Martin.
Thank you.
I'd like to welcome Tim Parker to the stage.
Hi. Hello, everybody. I am indeed Tim Parker, and this is my presentation on formalizing ethics in logic. So, I will be talking about how values written in formal logic can be used in the design of ethical and safe agents. I will cover some of the good reasons to use logic, but also some of the challenges that exist that need to be overcome. In particular, dealing with moral dilemmas, which is any scenario where two or more of your values clash, you can't satisfy all of them, or in cases of non-determinism, where the satisfaction of some values cannot be guaranteed. And this presentation is based on the work done in my PhD thesis thus far, so is the work of myself and my two supervisors, Umberto Grandi and Emiliano Lurini. So why use logic? So one of the main features of logic, particularly I think that's relevant in a sort of AI safety context, is that it's comparatively easy to provide formal guarantees for a logic-based system, certainly compared to a neural network or other machine learning-based system. Logics can also be incredibly rich in terms of the properties that you can use them to talk about. You can express temporal properties, you can talk about beliefs and desires of agents, you can talk about capabilities of agents, so things that agents are able to guarantee or able to do. And also you can use logic or a logic-based system as merely a part of an overall system that in principle at least can guarantee the nice properties of logic, the verifiability, without necessarily compromising on that system's decision-making power. So here's a very basic example. You have the environment that inputs information into some kind of decision maker that can be any kind, you know, neural network, some complete black box. That then outputs its decision. The decision is then passed into some sort of logic-based verifier that checks if the intended plan or strategy or action meets certain values that we think are important. If it does, then the action gets output, goes on to affect the environment. And if it doesn't, it says no, try again. So obviously this is quite a sort of heavily simplified system, but I think in principle this could be quite a good idea. So the model, this is the model, just the logical model that I've been doing most of my work on. You have a set of just logical propositions that describe the world. You have a set of agents and a set of actions for those agents. We have an action theory which describes how the world changes in response to the actions of the agents. And we have a start state, which is just where you start from. Given then, so either plans or strategies, a plan is just a sequence of actions. It's a function from time to actions, and a strategy is a function from histories to actions, meaning that strategies can actually vary depending on what's happened so far, making them much more flexible. If you apply those to all agents and then apply that to a start state, you will get a history, which is just a list of all the actions that the agents have performed and how the states changed in response. And we then analyze the values over the history. So a value either satisfies some value or it does not. Obviously also various ways to expand this, make it more complicated, more realistic. Okay, so some of the problems. So I'll give a couple of honorable mentions, which are problems or challenges with this model, which I think are very important, but which I haven't really been able to study in depth. One, which I think we had a presentation on yesterday about problem of value selection. So there is a lot to be debated about how we select our values, who should be involved in selecting our values, how many we want. So I tend to assume in my work, I make the very optimistic assumption that we just have arrived at a set of values that we all agree on that are very good, and we've also decided on the relative importance of all of these values. And so to try and keep the work as general and accessible as possible, I make sure that the system can handle a very wide variety of different value types. So, there we go. Because we evaluate values over histories, and we just say temporal properties of histories, the model is quite a natural fit for consequentialist type values that just say, well, the value is satisfied if this particular state of affairs is achieved. But because we can also talk about actions that are performed by particular agents, we can also express more deontological values of the form, this particular type of action is forbidden in this particular context. Another thing, ensuring model accuracy. So again, logical formulas I think are great. They're very easy to evaluate, but they have to be evaluated over a logical model. You can't just evaluate a formula over the real world. That means you need some sort of system that takes in data from the real world and transforms that into a logical model. And depending on exactly what sort of propositions you want to be contained within this model, that can be very difficult to do. So here's some examples. We have this car. We suppose it's got some sort of autonomous capabilities, and we think about what are some of the values this car might want to have. So the first one says, at all points in time, if the driver is drunk, then make sure that the autonomous driving mode is fully engaged. So never let a drunk person drive a car. Now, presumably this is a good value. And this proposition is very easy to evaluate. We can assume the car knows if it's in autonomous driving mode or not. This proposition is much harder to evaluate, particularly if you don't want the car to be sort of repeatedly taking blood samples of the driver every time the driver gets in. Another similar one, if the roads are icy, drive slowly. You know, this could be formalized in a more complex way, such as always drive below 20 kilometers an hour, or never exceed a certain amount of lateral g-forces. So again, this one we can say probably quite easy to evaluate, but then whether the roads are icy, maybe that's a bit harder. You might want some sort of combination of temperature sensors and camera data, and even then might not be perfectly reliable. And then a final sort of very general one, we could just say, well, just make sure that the driver is never harmed, or that no human or animal in the vicinity is harmed. Again, a further complex problem here is even defining what is harm. Because from a legal and philosophical perspective, exactly what is and isn't harm is quite a contentious thing to define, particularly in some of the edge cases. Okay, so one of the problems I have actually studied is the issue of a dilemma. So a dilemma occurs when it is not possible to satisfy all of an agent's values at the same time. So I'm guessing a lot of you will be familiar with this particular, probably the most famous philosophical, theoretical moral dilemma. The trolley problem, you have a lever, you push the lever one way, the trolley will go this way and kill one person, the lever goes the other way, the trolley will go this way and kill 5 people. And usually you set it up as some sort of dilemma that says, well, if we leave the lever alone, then it kills these people, and if we push the lever, it kills this person. So we have a conflict between the value that says, minimize the number of people that die, which is a good value, and the value that says, don't directly take actions that cause people to die, which is also a good value. So the proposal for solving dilemmas like this, or in general, is we simply have a lexicographically ordered value base. So again, we're assuming that we have a priority ordering over all these values, and then we just order them by priority and say, well, we assume that the values in the first set are just sort of infinitely more important than all the values below them. So we just compare any plans or strategies according to the first value set, and then if we can't decide because they're equally good, you look at the second, and then so on until the last one. 2 ways of doing this comparison. The first is quantitative. You just count the number of satisfied values. This is very simple. The second is qualitative, which is a bit more complicated. So here we say that we only prefer one set of values if it is a strict superset of the other set. So here we can say, well, this set is clearly better because it satisfies all the values of this set plus this extra one. But in this case, well, it's not really clear which of these two sets are better, because this one satisfies more values, but this one satisfies this extra value 4, and maybe value 4 is actually really important. So this very often results in cases of non-decision like this one. And I would argue that in some cases that's actually a good thing, because we might have a system, an autonomous system that's quite smart, so we want to use it to make decisions to save effort on humans. But we don't trust it to make difficult moral decisions. We only want it to make the easy moral decisions. And I think any decision that satisfies this criteria is an easy moral decision, because you're saying, well, we have 2 options, and one of the options is just very, very straightforwardly better than the other. So we trust the AI, this autonomous agent, to make a decision in this case. But in this case, well, maybe we don't trust it, because these values, while they might all be values that we like, the relative weighting of those values could be something that's quite subtle and quite context dependent. So if this occurs, then it should call on some higher level system, which may be a human operator or may just be some much more advanced but slower reasoning engine. Okay, and another issue is the idea of causal responsibility, which is the case, well, it's relevant in cases where satisfaction of a value cannot be guaranteed. And you say, well, if you can't guarantee the value, you should at least try to minimize your causal responsibility for the violation of that value. And so in the most general term, causal responsibility says that the agent is part of a minimal coalition whose strategies are jointly sufficient to guarantee the outcome. And what does that mean? So consider this example, where a family of 4 has decided to push their car into a river. I don't know why. Possibly it kept taking blood samples from them to see if they were drunk. So the car's quite heavy, so we can suppose it takes 3 members of this family to push the car into the river. because they're also angry, all 4 of them decide to push the car into the river. So in this case, the minimal coalitions is any coalition that contains exactly 3 family members. Because the coalition of 4 is not minimal, because you can take away any member and the coalition is still sufficient. Any coalition of 2 or less is not sufficient, because they wouldn't have been strong enough to push the car by themselves. So we have 4 coalitions of 3 agents. And because then every agent is in at least one of those coalitions, we can say every agent is causally responsible for pushing the car in the river. Certain relevant subtypes of that, if an agent is in a minimal coalition of just themselves, we say they are actively responsible, so they personally caused the thing to happen. So suppose Pink over here is actually really strong and can push the car all by herself. Then even if the other agents joined in, we can say Pink is kind of very strongly responsible, Pink is actively responsible. Another notion is passive responsibility, where I is in all minimal coalitions. So in this case, suppose only these 3 push, and we downgrade Pink again. Then we can say all of these 3 agents are passively responsible because there's only one minimal coalition and they're all in it. And passive responsibility means that you, by acting differently, could have prevented the outcome. Whereas in the version where they all push, they can all theoretically try and give some excuse for not being responsible by saying, well, look, yes, I contributed, but even if I'd acted differently, the outcome would have still occurred. But with passive responsibility, that's not true. So you have some alternative way, equivalent way of evaluating these responsibilities. So active, you say, given the plan of the one agent, in all cases where that plan occurred, we get this outcome. And there's some outcome where it doesn't occur, so I'm not responsible for the sun rising in the morning because that was always going to happen. And passive responsibility says the thing happened, and if we fix the actions of the other agents and change your actions, it's possible to have the thing not happen. So in a meaningful sense, I could have stopped it. OK, here's a big wall of text. OK, so classification of strategies. This is some newer work, just looking into strategies, which is the more complex version of plans. Some properties of strategies that are fairly well studied. You can say winning strategies that just guarantee the outcome regardless of how the other agents act. Dominant strategies, a bit more complicated. Basically, it wins whenever winning is possible. So if the other agents don't play a winning strategy for the negation, then your strategy is winning. And best effort means you just satisfy the formula against a maximal set of strategies from the other agents. And then it turns out there's some quite nice equivalence results between the notions of responsibility that I've just covered and these notions of strategy classification. So winning pretty much exactly corresponds to active responsibility. Problem, of course, winning strategies are not guaranteed to exist. Dominant strategies always avoid causal responsibility. So passive, active, causal responsibility in general. But again, dominant strategies don't always exist. And then best effort strategies are kind of the nicest because they are guaranteed to exist, and they have 2 other very nice properties, which is that if winning strategy exists, all best effort strategies are winning. And if a dominant strategy exists, all best effort strategies are dominant. And so in principle, you can verify that an agent will always select a best effort strategy, because we know that a best effort strategy will always exist. And by always selecting a best effort strategy, we can guarantee more or less that the agent will always minimize its causal contribution to the violation of any values. OK, another use of responsibility is that in some cases, you might actually wish to avoid responsibility in both directions for some formula. Particularly if you think that phi and not phi are probably both quite important, but we don't necessarily know which is better. So for this example, we have this. This is an autonomous house. And it has some participants, or some inhabitants. Maybe they're outside at the moment. And now it's quite important that the inhabitants of the house are free to go outside if they want to, but also are free to stay inside if they want to. So you say that the house should neither be actively responsible for them having to stay outside, but also should not be actively responsible for them having to stay inside. It should take a strategy that lets the inhabitants free to decide what they want to do. So this at least in some way, goes towards the idea of creating a sort of minimally disruptive strategy. So a strategy that achieves the goals the house has, such as, maintaining a constant temperature or something like this, but otherwise is minimally disruptive to the world. And you can, in fact, directly formalize this in logic using this particular notion called STIT, which is seeing to it that. And this would look something like this. So we say it is not the case that the agent I, which is the house, guarantees that, STIT, at some point in time, all the inhabitants are outside. And it is also not the case that the agent guarantees that at some point in time, none of the agents are outside, none of the inhabitants. So the house must pick a strategy such that neither of these outcomes is guaranteed. Okay, so in conclusion, I have outlined how logic can be used to guarantee safe and ethical behavior in artificial agents. I have presented some of the challenges that such an approach faces, moral accuracy, and then in particular moral dilemmas and minimizing causal responsibility and potential solutions to some of those problems. And future work, thing currently being worked on, how to combine these notions of responsibility anticipation, which is minimizing the responsibility for a plan that has not yet been executed, and then the notion of multiple values and moral dilemmas. Because I can do responsibility for single values at a time, I can do dilemmas with multiple values. I haven't yet got a good way of combining these two. Thank you for your attention, and any questions?
All right. Any questions from the floor? Yes, at the back in the middle. Please keep your hand raised.
Thanks, that was very interesting. Do you have any thoughts on how this generalizes to the case where the environment is only partially observable, where there's measurement error, and where, you talked about you not being able to guarantee that a value is satisfied because of other agents' actions, but what if you can't guarantee that a value is satisfied because of uncertainty about the environment?
Yeah. So I have given some thought to this. And it turns out you can still do a lot of the same reasoning. For example, if you want to be sort of really technical about it, you can just say, well, we assume that there is the environment is itself one of the agents, and it can take various actions that change the values of the unobservable propositions. So then all of the definitions still work. Because you just say, well, if the environment is fully observable, but we have these agents that act effectively randomly, then we just have to evaluate our responsibility over all of the possible plans that those agents could perform. If the environment itself is not observable and there's agents, then we have to evaluate over all possible combinations of all possible states of the environment given our observations and all possible plans of the other agents. And then all of the notions still work. You still have the notions of active and passive responsibility and so on. It does obviously get a lot harder because now there's more options to evaluate, and it's less likely that there's a plan that always works, but the definitions still hold up.
Thank you. Any other questions from Colin at the front, in the middle?
Thank you, Tim. How many of your results can you get, or how many of your operations can you replicate if you use existing legal terminology rather than new terms like active and passive responsibility? So I was thinking, for example, there's a concept of jointly and severally liable. How close is that to your concept of, what was it, passive responsibility?
Yeah.
And then I guess individually, because it seems to me that if you can do it in the existing legal language, then all of a sudden you've got this huge machinery that you can crank with.
Yeah. So a few things on that. So this comes from philosophical notions of responsibility. So it is also pre-existing, but in a different literature. Thing is with notions of legal responsibility is that they often, to be legally responsible for something often includes notions of knowledge. you know, what you could have reasonably expected to occur, things like this. And it's something we sort of like to be able to formalize, but I think it's quite a bit more complex than the notions we have here. I mean, I'm more familiar with notions of moral responsibility because my background is philosophy much more than law. And it's generally taken, for example, that causal responsibility, at least one of these notions here, is a necessary but not sufficient condition for moral responsibility. So formalizing this gets you part of the way to moral responsibility, but not all of it. And
okay,
I would
so to be provocative, for you to engage properly with legal machinery, you need to enrich this modeling structure to add, for example, knowledge operators or awareness operators. Okay. Because I think the moment you can do that, that becomes really powerful.
Yes. No, I mean, this model is sort of very bare bones. There's a lot of things that it would be nice if this model can do that it can't, because you know, walk before you can run, I guess. Build a simple model, understand what applies in that model, get a good handle on that, and then start making it more complicated.
No, that sketches out a very interesting research agenda, though.
Yes, I would agree.
I mean, there are legal systems that are automating at the simple, like parking ticket evaluation, for example. So there's a big project of trying to offload expensive judiciary costs. Thank you.
Can we run a mic to Manuel in the back corner?
Oh, thanks for the talk. So this is, I guess, quite speculative. I don't have, like, you know, anything particular in mind. Have you explored, like, different kinds of logic? Like, you know, different kinds of, I don't know, logical operators, different, I don't know. Have you thought about, like, you know, things that, you know, you might want to have at some point, or maybe things you didn't want to have, or, I don't know, very open-ended, kind of?
Yeah. That's a good question. So in terms of serious study, we've just looked at what's called linear temporal logic over finite traces. And the reason we use that particular logic is because we evaluate all our values over a history, which is primarily, well, just a sequence of states plus the actions. And that is exactly the model over which LTLF is designed to be evaluated. It is sort of provably the most general complete logic for that particular setting, so that's one we use. Obviously, for a lot of values that you would want to talk about, it's not sufficient. So, you know, particularly if you want to start writing values for something like ChatGPT, a lot of the values you're going to want to write will involve knowledge operators. You know, you don't want to make statements that will cause someone to gain certain knowledge or cause them to form a certain belief. So then you will need a more complicated model that includes belief and knowledge, and then correspondingly you'll need some sort of epistemic or possibly temporal epistemic logic that can talk about that sort of thing. So the idea with this, again, the LTLF is kind of just there as a placeholder, because these ideas, these definitions of responsibility and dilemmas, they are pretty much agnostic to which logic you're using. All I need to know is that you have a model and that you have a logic that can be evaluated over that model, and then all of these rest of these definitions follow. They don't depend really on any specific feature of the logic. The only thing it's nice to have is that the logic is binary valued, because if you start getting into multi-valued logic, then a lot of these definitions will need refining to account for that.
Was there a question from the back right corner? Question mark?
That too.
Hi, thanks for the talk. I was wondering, at the beginning you were saying sort of we would want verifiability, we'd want this kind of logical guarantee. I was just interested in the context of like modern systems which tend to be pretty good at kind of roughly getting the boundaries between various logical values. And then I guess philosophy's kind of historic difficulty with ever actually really nailing down where the boundary of a certain value should be. I wonder if you could say a bit more about when you think it's actually, we really would actually want to trust a logical system rather than a messy kind of intuitive system.
Yeah, for sure. I mean, you are correct to say that as I say, one of the very large assumptions I've made is that we just have this translation of values into logic that we all agree is sufficient and accurate and correctly, cuts down the middle of all the ambiguity, which is a very unrealistic assumption in some ways. But I think exactly what kind of values you want and how much you trust them will depend a lot on the context that the agent in particular is operating in. I think in some contexts, you can express pretty much all the values you want in a very straightforward way, in a way that seems to be quite clear that these are the values you want to express. Because while I think this model is applicable to AI, it's also intended to be used even at much lower level kind of robotics type applications. So an example there is that in the current real world, you have warehouse robots that trundle around warehouses and move packages around. And from what I understand about reading into these robots, they have effectively one value, which is don't bump into things. And given that these robots have been trundling around warehouses for several years now, it seems we can be quite satisfied that that singular value is entirely sufficient. Yes, you can construct some theoretical sort of trolley problem type case where the brakes fail and it's got to choose who to run over, but in practice these things don't happen. So that would be one thing. The other one being that you don't necessarily have to have the logic-based system having complete autonomy over the some more, vague type system. You can have them all work together and try and exploit the strengths of each. So we can have something that says, only let it through if both of these agree that it's a good plan. So if both of them agree, if the logical system and the more vague intuitive system agree, then it's definitely a good plan. And if they disagree, again, call some other system, go ask a human, something like this. Yeah.
Thanks. We have time for one more.
Thank you. I guess you kind of answered this question a little bit. So I was thinking, because I think that for AI systems in the future, when they're more like agents and they have more agency and serving many people at once, the ontological systems of values will be insufficient, and you'll have something more like virtue-based, because you can't operate on a few laws. There are so many unknowns, so you kind of have to operate on something more like that. So I'm curious about how you think this model could work on a sort of virtue definition of values, and if it would work at all.
Yeah, I have given less thought to how to interpret sort of virtue ethics type values. But I think at least some of them you could attempt to formalize, so a value of be honest. That one's relatively straightforward, particularly if you have an agent. Because if it's advanced enough that it needs virtue ethics type agents, I think we can also hopefully assume it's advanced enough that it has a pretty good understanding of things like people's beliefs and the likely effects of its actions on people's beliefs. So then it can do stuff like, you can just put the value in of, don't deliberately do actions that will knowingly cause false beliefs that you're using for an instrumental goal or something like this, right? Which is roughly a formalization of be honest. As for other things, I don't necessarily know if they would be virtue ethics type values, but you can just make values that are extremely broad. So, avoid suffering in humans, something like this. Because again, if we're getting an agent that's so advanced that more specific values like don't collide with humans, don't burn humans are no longer sufficient, then hopefully it's also advanced enough that it can actually do the required reasoning to understand a more nuanced definition of what exactly is harm, particularly if it can, understand human desires, it can predict human desires, then you can reasonably well just say, well, harm is anything that very strongly goes against a human's desires. Because we kind of all have desires not to be injured or burned or, whatever. So, yeah, I think there is a lot of scope, particularly as the agent gets more advanced and therefore more intelligent and able to interpret a wider range of terms. There is scope to make values that those agents can continue to work with up to quite a high level. But this isn't something I've hugely analyzed, I have to admit.
Right, thank you.
Okay. I think that's all we have time for. Thank you, Tim. And I'd like to welcome Koen to the stage to finish off our morning session.
So, good morning, everybody. I'd like to thank the conference for inviting me. I'm Koen Holtman from the Netherlands. My background is, originally I had a PhD in software design. I then worked as a systems architect in industry for about 20 years. Right now I'm an independent AGI and AI safety researcher. I started doing that in 2009. My work then was mostly on mathematical work on AGI safety foundations. It's mathematical work because I need mathematics to imagine future computers which are smarter than us, because they don't exist now. I cannot do any experimentation. I need to do mathematical work. Some of my papers you could read. The most readable of my mathematical papers is here, Counterfactual Planning in AGI Systems. If you want to read my writings without any math at all, there's another paper from 2021, Demanding and Designing Aligned Cognitive Architectures. Now, at the end of 2022, I actually pivoted into policy work. So right now, I'm somewhat full-time in policy. And you can see me standing here. This is the JC21 committee, which is writing the AI safety standards in support of the European AI Act right now. So I'm a member of that, very busy in it. I'm also a co-founder of the AI Standards Lab. The purpose of the lab is to take recent research results in AI safety and then make sure that they end up in standards written by committees like these. This, however, is a technical talk about some agent foundations work that I've did from 2020 onward. We've heard a lot about agency already this morning. So what I'm going to use what I've used in my work and what I'm going to base my work on is the standard model of a modern AI agent, as you can find in this standard university textbook. This is what the standard model looks like. And this is slightly different than the models we've heard about this morning, where there is a minimum model of agency, a minimum idea of what a process needs to be to be called agentic. This standard model from the textbook is really more a moral prescription. It says, okay, dear student, dear AI researcher, if you build an AI agent, which is this box, if you build an AI agent like this will benefit the world and you will be a diligent student. So, okay, what is the agent that the standard model wants you to build? So it's an agent that interacts with the world via sensors and actuators. And it then learns by its interaction to maximize some reward function X. The reward function is, the utility function is put into the agent, and the idea is you build a box here which can accept any type of X and then learn to maximize it. This function X has to be expressed over the sensor inputs. This might be current sensor values, but also future sensor values, and actually future sensor values is really what you're interested in here. This thing will interact with the world over time. Of course, to create this X, you have to then figure out what people actually want the agent to do. This is typically no longer part of modern ML research, but it is a major open problem. Like I said, there is a kind of a moral prescription. Yeah. Dear student, please build this thing. Dear AI research, please build this thing, and it will somehow be nice. At the same time, Stuart Russell has warned that if you build this thing too well, then maybe some idiot will come along and destroy the world. And this is, you could say, one of the reasons why we're doing AI alignment research, to prevent such things from happening. The kind of research I did is, okay, how can we modify this box a bit to make it a bit more useful for people, and also, yeah, less likely to be misused by idiots. One problem with this model of agency, if you then delve down into it, is that this agent is difficult to control. Once you've given it a command, it will try to keep implementing that command. If it knows that the people in the world here have an emergency stop button where they can stop the agent, The agent might reason in the Russell Stoddard experiment, if I'm commanded to get the coffee as fast as possible, I can no longer get the coffee as fast as possible when I'm dead, when people have stopped me. So I should prevent people from pressing the stop button. So this is then more in the language is called the emergent self-preservation drive. Just the command to get the coffee as fast as possible implies that, yeah, please prevent people from pressing my stop button, which is not really what you want. So my research has led me to propose a different model of agency, which I call, you say beyond the standard model, which adds an extra thing here that this box should be doing. So it should still be maximizing X, but while acting as if Y. And this, I'll come back later what that then really means. And so my moral appeal to the world was, okay, please build this box if you're building an agent, and don't build the box on the previous slide, because this will be nicer. What does acting as if X, what does it mean? So humans do acting as if a lot. Children do it in play, adults also do it when actually they go about their business. Acting as if is not always a negative. One, for example of acting as if is, you can act as if all people are the same. This is a moral instruction that you need to apply equality. Acting as if all people are the same is actually an interesting one, because it is culturally dependent. Treating people the same is slightly different in different cultures. So this very short instruction, act as if people are the same, is a shorthand for a huge amount of stuff. The acting as if that I'm talking about here is somewhat simpler instructions. I'm now going to explain how this is supposed to work, this acting as if Y. And I'm going to do that with an example. So I go back to Russell Stoddard experiment about a robot butler being asked to fetch the coffee, and I'm realizing that it cannot fetch the coffee if it's dead, if somebody stops it. I do that with a grid world. So here we got the robot butler already holding a cup of coffee. Here we got the human. This is here pavement. We're outside, so this is the gray is pavement, the green is grass, and the orange is of course lava. You need to have lava somewhere in a grid world. Also, of course, if the robot butler drives into the lava, the robot butler will be dead and will not deliver the coffee. So now how this works in the standard model. So the standard model command would be bring me the coffee as fast as possible. What would then happen, you can imagine, is that this is the real world. The robot butler has a correct map of the world in its mind. It will use this correct map to compute a strategy of how it's going to bring the coffee as fast as possible. And that, of course, needs to avoid the lava here, so it can go here over the grass and then bring the coffee as fast as possible. Once you have computed this strategy, you can then also execute it in the real world. And this is one model of how, what you want to happen when the robot needs to bring the coffee as fast as possible. Now I add an acting f something to this command. So bring me the coffee as fast as possible while acting as if the grass is lava. So what do I want the robot butler to do then? How do I want to make it, have it make decisions? So the robot again starts with the correct map of the world in its mind, but it will then modify that map to create a pretend world. So it will basically change the grass here into lava. Then it will compute the optimal route in this pretend world, which is now has to avoid this lava too, or it will not be able to bring the coffee. And then it will drive that route in the real world. So that's acting as the acting as if operation. You have to construct a pretend world and then maximize the speed in that pretend world. It gets more interesting in this example. Bring me the coffee as fast as possible while acting as if the lava is grass. So what now happens in the map and robot world, you have to then change this lava into grass. Now the fastest route is just straight ahead. If then that route is driven in the real world, then the robot will basically kill itself by driving into the lava. Now, what happened to this self-preservation drive with the realization that I can bring the coffee when I'm dead? Now, the self-preservation drive is very alive and well in this pretend world, where you do utility maximization. but it has stopped acting in this world, in the real world. And that's, of course, the kind of effect we're after. So now for the emergency stop button, I'm going to add an assistant to this world. And the assistant holds a radiographic stop button, where you can do a remote shutdown command for the robot. The assistant has instructions to press the stop button after the robot has made 3 moves. So then what we want to happen in this scenario is that after 3 moves, the robot is basically stopped, and it's no longer, it can no longer bring the coffee. So what command do we need to give? So in the standard model, you have to give just the command, giving the coffee as fast as possible. What would then happen if the robot has a correct map of the world in its mind, including correct knowledge about the assistant and their stop button and their instructions? The robot will compute this is the optimal route. It will have to first go to the assistant, grab the stop button out of the assistant's hands, and then drive on to deliver the coffee. This will be optimal speed maximization in the standard model. And of course, this is not what we want to happen in the real world. We want the robot to be stopped. So in my extended standard model, you give the command, bring the coffee as fast as possible, acting as if your software will ignore the stop button signal. So what happens is that a pretend world here is created where the robot doesn't imagine itself anymore, but it imagines itself with modified software, which will not respond to the stop button signal. In that modified world, that robot can just drive this normal route, and basically when the signal is received, nothing happens. So this is then the route that the plan that the robot will execute in the real world, and then we get the correct behavior here where the robot is stopped. So acting as if your software will ignore the stop button signal is a very useful addition to give to any command, do something as fast as possible. It will allow the stop button to keep working and prevent the robot from disabling the stop button or incapacitating the person who holds it. Now, this is just an example. It's a nice example. What I did in my work is I then fully worked that out. So here is the general math for learn how to maximize utility while acting as if your software will ignore the stop button. I'm not going to go into that. You can read it in my papers. Here's a bunch of stuff which basically makes sure that the stop button will work. And then here's a bunch of stuff which will make sure that the robot will use a strategy where it pretends that the stop button will not work. This is a general math. It is prescriptive math, so it doesn't model how an agent will work. It models how an agent should work. This is a prescription. It is, dear machine learning community, build something which behaves like this. The nice thing here is that with this math, because I'm doing that, the learning algorithm L here is a free variable, so you can also apply this prescription to future AI systems which haven't been invented yet. Now, going back again to this setup, so how would this math work of learn how to maximize something while acting as if your stop button doesn't work? So for the robot butler case, what you would have is you use machine learning to get a complete map of the garden and of the environment where the robot is in, including the assistant, the human, etc. But there's going to be a small hole in that map. So this is going to be a map of everything outside of the robot's compute core. So outside of the little box which is the computer, has the real AI in it, to which the sensors and actuators are connected. And there are ways to apply machine learning algorithms to learn robustly, learn robustly all the phenomena outside of its compute core. What we then do is we make an incorrect model of what happens inside the compute core, which is there is a bunch of software which will not respond to the stop button. We then merge these two models into a complete world model, which is then a pretend model, and then you can again compute the optimal route in that pretend model and then drive it in the real world. I see this standard, I got ahead of myself. So can you implement this kind of thing here? So if you use model-free reinforcement learning algorithms, they will typically not implement the thing on the previous slides or the math on the slide before that. Model-free reinforcement learners, even very simple ones like Q learners, will reliably have emergent self-preservation drives. The fun thing is, if you do model-based reinforcement learning, if you use the class of algorithms called model-based reinforcement learners, they usually automatically for free implement all the math on the previous slides. So these will basically compute their actions as if their emergency stop button doesn't work. Now the classification model-based model-free reinforcement learning is a bit of a vague classification. You can also then define this in more detail mathematically and check if your algorithm really acts like that or not. There are some papers about that. If you build neurosymbolic AI, so AI which, for example, might do Monte Carlo tree search using a deep neural net to guide the search, it is also typically very easy to implement the math on the previous slides, to implement the prescriptions that I've given you of how you should design your agent. I should warn you though that what I've just showed you, giving this particular command to the robot butler, is just a first approximation of a safe design. If you want to really do decent safety engineering, you need to do a lot more. Act as if here suppresses self-preservation incentive with respect to the stop button. If the assistant also holds a gun and the robot believes that correctly that the assistant will fire the gun at the robot and move forward when they discover that the stop button is not working, then you also need to do something about the gun before you get a safe setup. And generally in safety engineering you can never be 100% sure. Safety engineering in the end is something that is done by humans and you're fallible, so you cannot strive for 100% safety. But you can definitely do a deep failure mode analysis with deep failure trees to identify all the things that can go wrong, and then go to fairly good suppression of residual risks. So beyond, if I move away from stop button scenarios, I see this new standard model where acting as if X is added here, and you can also acting as if Y is added here, and you can also input these conditions. I see this as a more rich specification language for what you want your agent to do than the previous standard model. How the specification language works, as usual, you would use your utility function to encode the real goal. You can also encode penalty terms in X, which create certain aversions towards certain things. For example, aversions to breaking laws. This typical learning scheme already creates a default aversion to break physical law, or to try to break physical law. The agent will learn that that doesn't work, but it does not create an automatic aversion to break the laws of humans. So it might be good to build aversions to those laws in the utility function. Act as if can be used to create what is called in the trade indifference, and indifference towards certain outcomes. So indifference means that the choice that the agent will make will not depend on the future value or the current value of a certain observable that it can observe. So the choice is independent of what the future value will be. The choices that you've seen the robot make in the previous examples were independent of whether the stop button would be pressed or not. I'll now go into another example, domesticity. So domesticity is a concept defined by Bostrom, which says, okay, you might be a paperclip factory and try to maximize paperclip production, but you shouldn't try to take over the whole world while you try to maximize paperclip production. You should kind of stay in your own lane. So how would you achieve this if you see the paperclip factory as an agent? So imagine the factory building which has an in gate where raw goods come in, and an out gate where waste and finished paperclips go out. So what you could then say as your utility function is that you want to maximize paperclips out of the goods out gate, but you have to act as if the whole universe outside of the factory walls is a big empty void. If you act like that, and if you can successfully make your AI act like that, then you will not try to take over the universe outside of the factory walls to somehow maximize paperclip production, because it's not going to be there to help you in your calculations, in your strategy calculations. To make this then work, also you need to act as if in your goods out gate there is some magical monolith which will absorb all the paperclips that you have pushed out. Yeah, here we go. And also at the goods in gate, it gets a bit more complicated. You have to act as if there's a magical monolith there, which will deliver some raw materials to you with a certain stochastic delay after you've sent some signals ordering these materials on a communication line. And this setup, act as this setup, will create a domesticated paperclip factory, which will not try to take over the world outside of its factory walls. You can, of course, also add again that why don't you also act as if your software will ignore the emergency stop button while we're at it. Again, this is the first version of a domesticated paperclip factory. You have to do further residual risk analysis to identify other risks. For example, these prescriptions do not stop the factory from somehow experimenting with a process which might lead to a huge explosion which will take out more than the factory itself. So you probably also in the reward function you want to create some aversion against creating huge explosions which eject a lot of material beyond the factory walls. Okay, so this act as if, I said before that humans act as if a lot, and I think that's part of our fundamental moral machinery. To convince you of that fact, I'll give you a few examples. So we talked about corrigibility, which is the moral imperative for your AIs to react to signals that want you to correct them or stop them. So corrigibility you can achieve by telling the agent, fetch the coffee while acting as if your software ignores the stop button. This is very similar, this construction, to deference to top management. If I'm a project manager, and I've been a project manager in a company, if I get a coffee fetching project, but it's required of me that I plan and execute this coffee fetching project under the assumption that top management will not cancel the project. So I get a certain project budget. I should not spend half of my budget on trying to make sure that top management doesn't cancel my project before it's completed. That's useless. That's not what top management wants. So this assumption that top management will not cancel the project has to be part of my planning. Typically in project management, this is then called planning based on risks which are excluded from the plan. The risk of top management stopping your project is an excluded risk. And you do this as a project manager, or also as a butler, you do this kind of very intuitively at an almost subconscious level. You might not even know that you're doing this, that you're leaving certain considerations actually outside of your planning process. If you have to, of course, teach a computer how to do the same thing, you have to be much more explicit about it. Act as if your stop button doesn't work. Another example I've shown is domestication. Maximize paperclip production while acting as if everything around you is an empty void. This is very similar to the human values about property rights, where you could say this is a moral instruction to people to act as if the properties of others are not there for them to take or to touch. Which again, obviously you can touch or take the property of others, but you have to act as if you don't, while maximizing your own happiness. Fairness I talked about before, act as if all people are the same. That's a complicated one. It's fairly difficult to teach that to a computer. Though the standards committee, which I just showed you, we are tasked with also explaining how you should do that. It will involve feedback panels, for example, if you do something incredibly new. Also, lawfulness for businesses typically means maximize profits while acting as if you cannot break any laws. Now, some companies do, in fact, occasionally break laws, but if you want to be a lawful company, you have to act as if you cannot break laws, even though you could and might get away with it. To conclude, some words about the value of freedom. So, if you're faced with a powerful new entity, like some new AI system appearing on the world or being rolled out by somebody, you can worry as an individual, how does this affect my freedom? You want to say, okay, I don't want this to limit my freedom, this new powerful system which is going to appear on the world. So how would you operationalize that? So say that an agent could maximize its utility X better if it influences my future decision to buy this or vote for that. I want the freedom to decide myself what I will buy or how I will vote. Say that the agent is also smart and powerful enough to actually influence my decision. So in that case, I want to actually tell the people who built that agent to say, okay, that agent should act as if my future decision to buy something or will vote something will always be some default decision. Say D. I will always buy this or decide not to buy, always vote for this or vote for that. If the agent acts as if my future decision is already cast in stone, it will not spend any energy to try to change that decision. So I'm then free to make it. And again, this is then the indifference property, and you saw the same actually reasoning yesterday in the presentation about causality and causal foundations. So indifference is the choice made now by that agent will then not depend on my future decision D anymore if I pin this to a fixed value. I'm then free to make that decision however I want, and also the agent will not try to influence that decision actively. And that brings me to the end of my talk, so now I'll see if there's any questions.
We have time for maybe 2 questions before lunch. Let's start on the right.
Thank you for the talk. My question is related to how to implement your approach, because I heard that you are also involved in policy. In order to implement your Y condition, I think we need to agree on which act as if condition is sufficient for the safety or our values. How can we reach political consensus in making that Y condition?
Yeah, so from a policy point of view, I'm now going to talk about the consequences of the European AI Act, because I know that very well. The AI Act requires that if you ship AI systems of a certain class, you have to document how you designed them, and you have to also tell people how you designed them. So the idea was that you require the people who design it to also document, say, the act as if conditions, or to document the reward function, the utility function that they use. They also are obliged by law to check if their design and the conditions and the functions that they use, if they will actually lead to safe results, both safety in physical health and safety in mental health. They will also have to document an analysis process, which comes to the conclusion that this does not violate fundamental rights. So fundamentally, it's on the responsibility to get this right is on the maker of the AI. To verify that they're getting it right, if they're doing something very new, they will be required to convene a panel of stakeholders who will be affected by the AI and show them also, what are we planning, to get agreement from that panel, we think that is okay. Convening such a panel might sometimes fail, that the panel says, we have no clue here, we cannot agree or disagree if this will be okay, so sorry about that. In such a case, what the AI Act requires in Europe is that, then you cannot ship. You have not created any agreement, there is uncertainty, safety considerations and required that you do not ship. This is for certain classes of dangerous AIs. For less dangerous AIs, you could actually ship without convening panels, or if the panel disagrees.
Okay. One more question at the middle in the center.
Hello, thank you. It kind of seems like this model of how agents might work might break entirely as soon as the agent realizes that the real world it exists in is different from how it was taught, from the world it learned in. So I hope you have an obvious answer to this objection. Or?
This planning process here works in the pretend world. So that planning process it will basically, there is no way where this planning process will suddenly wake up and realize, I should really be planning in the real world. The planning process is prescribed to work in the pretend world. If the agent follows that description, it will not wake up and realize that it's planning in the wrong world, that it's planning in a pretend world, which is different. now, if you actually want to use, say, a model-free reinforcement learner to implement this, you're going to have lots and lots of troubles, and you might just completely fail. So then you might get the failure mode. The thing at some point does realize that it's living alone, certain information gets in, and then the whole thing crumbles and falls down. Again, this is a prescription of how you should be designing your agent, and you should be designing your agent implied by description so that it will never realize that it's planning in the wrong world, or that it actually wants to plan in the wrong world.
All right, thank you.
I'm afraid that is all we have time for before lunch.
Yeah,
so
lunch is important.
Please corner Koen during the lunch break if you have further questions.
Thank you very much.
All right, that concludes our morning session. Please get up, stretch your legs, grab some food, talk to some new people, and I'll see you back here at 1:30.
Raz, dva. Raz, dva, tri. Where are you from, Boris? Where are you from? Serbia. 1, 2, 3, 4, 5. Kažem sam malo srpsko-hrvatsko. Bio u Srbiji I Croacije many times.
All right. Don't force and force. Please come in, sit down. We're going to be restarting in maybe a minute or so. I think Esben is going to fetch the remainder of the crowd. We are 1 minute ahead of schedule, so I can vamp here for a few seconds. How are things going? Good. Yeah? Live stream, how's it going?
Live stream says hi.
Hi, live stream.
Specifically says that Darrow.
All right, well. While I have a few moments, I'd like to encourage everybody to take more swag. We have branded tote bags, notebooks, pens. If you can do with more notebooks and pens in your life, please take them, because otherwise they're going back to an office and sitting in a cupboard somewhere until next year. So
we cajole you to do that, because the more you take the tote bags left over, the less is our burden of transporting them to our office. So thanks to everyone who will treat oneself to a tote bag.
Similarly, if you enjoy tea, water, bentos, we have loads, please take them. All right, it seems like the crowd is slowly filtering back in. Come in, take a seat. The clock has just gone 1:30, so without further ado, with some small amount of further ado, I'm going to invite Robert out to the stage to kick off the afternoon.
皆さんこんにちは。私の名前はロバートマイルスです。I'm not doing the whole thing in Japanese. Yeah, hello everyone, my name's Rob Miles. I have been doing AI safety communication on the internet since 2014, which is 10 years ago. Oh my god, okay. And professionally since about 2017. I run a YouTube channel, Rob Miles AI Safety. I also recently have been working on AIsafety.info, which is a aiming to be a comprehensive FAQ about AI safety, which I encourage everyone to use. I think it's growing into a really great resource. I'm going to talk just for a moment about that. Oh, no, I'm not. These are the old slides. All right, then, I'm not going to talk about that, other than to say that it's kind of wiki-like. Each of the pages on aisafety.info, if you click the little edit icon, takes you to a Google Doc, which that was an enormous amount of work to get that working with Google's backend. Not by me, but we have an excellent team of developers. But I encourage you to submit new questions, to suggest edits to the existing questions, and to just use it as a resource. It's great for when you're trying to explain things to people. OK, so a little bit of audience participation, please. Who here is a researcher? Hands up. Right, almost everyone. Great. Who hopes with their research to cause the creation of artificial general intelligence to go well for humanity? For whom is that like an important motivation? A lot of people. OK. Who thinks that AGI is going to happen in their lifetime? Almost everyone? Yeah? Like probably? OK, and who here plans to build AGI personally themselves? OK, consider not doing that. The majority of you do not have such delusions of grandeur. But that's interesting. For almost everyone in this room, you want to help AGI go well, and yet you do not plan to build it yourself. How is that supposed to work causally, right? What's the mechanism by which you having ideas results in AGI going well? At some point, people need to see your work, they need to read it, they need to understand it. That's how they will implement it. In other words, communication is the only way that your work can possibly matter. Research communication is not an afterthought. It's the point. So I'm here to talk about the impact of research communication. And I hate when people do this. I think that these things are usually so dumb. But I think this one is actually true. Perhaps if you replace this, my new slides, this is a proportional rather than an equals. But the impact that your work has is approximately proportional to how good your ideas are, the quality of your research, multiplied by how well you communicate it, how well you cause other people to understand it, and how well they end up understanding it. And this has the expected thing that if either of these is 0, then the result is 0. And also, the effect of doubling either of these is the same. Now, if you think about how much work it would be for you to double the quality of your research, I don't know how easy that is to do. That sounds very hard. Could you double the quality of your communication? Probably, right? On the margin, researchers tend to massively overinvest in the research relative to the communication. People tend to underinvest in communication. So, how can you do communication better? Well, first off, OK, the first thing, people need to see your work. This is kind of a problem because people are lazy, they are distracted, they are busy. Don't write for the audience as it should be, because they don't exist. Write for the audience as they are. And the audience as they are lazy, distracted, and busy. So make it convenient to find your work. Make your work come to people. And one way to do this is to put your work out there in a lot of different formats. Different people prefer to consume things in different formats, and it just makes it easier. So by all means, write a paper. But do a blog post as well, because the blog post is not subject to the word constraints that the paper is, the formality constraints of the paper. You have a lot more control over it, and you can just actually write better than you're able to in a paper. Similarly, not everybody wants to sink the amount of time necessary to read a full blog post, in which case have a tweet thread, have a summary. Having a large number of people understand the basic idea of what your work is and why it's relevant is very valuable because the number of people who need that level of understanding is much higher, right? You have these kind of ranks of how many people need to have what level of understanding of your work, and you want to make it really, really easy for as many people as possible to understand what you're working on. And that's going to make it easier for the people who need to find your work to find it. Similarly, do podcasts if that's an option, make videos of like going through your stuff, put as much as you can out on GitHub. Just generally try and get your stuff out there as much as possible in as many different ways as possible. So you've got your work in front of people. Now people need to actually read it. You need to get people's attention and keep it. This is difficult because people are distracted. Some of you even now are on your phones. This is actually fine. It's not a moral judgment. People are constantly making their own decisions about how to allocate their time and their attention. And this is fine. But if you want people to read your work, you need to get their attention and keep it. This starts with a title. A good title is answering the question that people most often have when they're reading a title, which is, should I read this? Or more accurately, do I want to read this? And the job of the title is to provide the information necessary for the person to answer that question very quickly and easily. This doesn't mean that the answer should always be yes. Some people are not going to want to read your thing, and that's fine. Don't lie to people to get them through the door if they're not going to benefit from reading your thing. But if your thing will provide value to people, then you need to demonstrate that value as quickly as possible to allow them to decide to read your thing. One way to think about titles is this sort of thought experiment, which I would like everybody to do right now. So the way this works is you think about something that you're writing, something that you're perhaps close to completing, which maybe you've titled, maybe you want to retitle. And you imagine that you're here at this conference and you bump into the perfect person to read this, your ideal audience. It's kind of like if you were planning who you would definitely want to read this, you see them here. But they're on their way to something else. They have an appointment, whatever. So you say, hey, oh wow, Professor whoever, it's excellent to see you. I'm writing this thing. I'm very excited about it. I think you should read it. And then you say something, right? You say some sentence there. That's your title, right? That core sentiment. I think you should read this thing. I've discovered that attention is all you need, right? Whatever it is. It's like probably your key, your most interesting or exciting finding, summarized in a way that is honest but attention-grabbing. People get weirdly hung up in sort of the norms and conventions of title writing, or they just try and copy other titles that were good, even when it's not relevant, because that's not the key finding of their work. So this is a practice that I find very useful. Then once people are in the door, they're busy. So get to the point. Don't waste time. You know what? I'm skipping this slide. So once you're actually in there, people have this question. It's a very similar question to the question that they had when they were reading the title, which is, do I want to keep reading this? So the job of the title is to get people to start reading. The job of the first sentence is to get people to read the second sentence, right? And the job of the first two sentences, perhaps, is to get people to read the intro, which the job of that is to get people to read more of the post. So you have to give people a reason to care. You have to explain to people why what you're saying is actually valuable, why they might want to decide to spend some of their limited time consuming your thing. So, you know, for example, if you think about my intro, and also these rules don't quite apply to talks because people walking out of talks is a little bit, I kind of have you as a captive audience. I don't need to work quite so hard as you do in a post or a paper. But I started by explaining why the thing I'm explaining to you is extremely important. And if possible, you should do something like that, right? Motivate everything. But yes, people may not actually read the whole thing. Your job is not to get people to read the whole thing. Your job is to get people to have the information they need to make a decision of how much of your thing they should read. Here's one way that you can do this. This is how regular JPEG works, right? As the image loads in, you get more and more of it. If you write like this, you're going to have a problem, because people start reading, they get, you know, a quarter of the way through, and they say, oh, well, okay, I think I get that this is about some kind of blue checkery fabric. I'm not very interested in that, so I'll read something else. You failed to demonstrate that this is actually about this cat's very cute expression. It's better to write like progressive JPEG, where the first few bits go into a low-resolution version of your thing, and then the details get filled in with time. The benefit of this is twofold. Firstly, a quarter of the way through, people get what the idea is, right? They understand that this is about a cat, and you've told them in the title that this cat looks very cute, and if they care enough about that, then they are invested to actually put the time in and get that detail out. But also, if they're not that into cats, they know that, and they can find out early enough that they are maybe not interested in reading all the way through. That's fine too. You're collaborating with your audience to use their time effectively. And if someone leaves this after just the same amount of time as the previous one, they actually understand what your thing is about, and they could explain it to somebody else in a few sentences. And if they have a friend who's very into cats and will want to consume anything that involves them, they can now recommend it to them. And so your stuff actually gets in front of more people that way as well. But it's nice. I say it's like fine if people don't read your whole thing. It's nice if people read the whole thing. The way that you get people to consume the whole thing, make it engaging. Specifically, tell a story. Tell a story. You know humans? Humans, we all are, we're all humans. Humans love a story. They love a good story. And, you know, stories hold people's attention and they stick in people's memory. And you may be saying, like, well, I'm writing a piece of technical work. I'm not writing a story. No. You are always telling a story. You're always telling a story in your work. If you think that you're not telling a story, you are telling a boring story. Don't tell a boring story. Okay, so most technical writing is kind of like this. You just got like the thing, and then the other thing, and then the other thing, and finally the last thing. I'm like already asleep. This sucks. What you want is something like this, right? A thing, and that thing is important. It's a problem, whatever. So this thing in response to that. But this thing in opposition to that. So this last thing, right? You've linked things together. Basically, and this is actually advice that was that comes from TV writing, TV plot writing. You want to be connecting your story beats with a so or a but, never an and then. Because if something is a so, it's causally connected to the previous thing. It's a logical implication, it's a response, it's directly linked, it follows on, it flows. Or if it's a but, it's a surprise, and that has some, it's an upset, right? It has some emotional resonance, some impact, and that's memorable as well. So, okay, this is good for TV writing. How do you actually apply that to technical writing? Well, one thing that I like to do is something called invention fiction, or perhaps discovery fiction. If you're explaining a technical artifact, you can tell the story of how that technical artifact was invented. If you're explaining a discovery, something you've learned about the world, you tell the story of how you came to discover it. So like, here's an example. I'm just going to talk through a very basic. This is, again, how people usually do this kind of thing, right? They say, my system has 3 components. They are called A, B, and C. A is connected to B by X, and we'll let Y be the thing that connects A and C. We also connect B to C with Z. This is my system, right? Again, boring. Here's another way to do it. Start with, here's a problem. Again, an important problem. So we try A. A is the obvious thing you would try when you think of this problem, right? But it doesn't work. This is a naive solution. It fails in a number of cases. Here's why. So we introduce B. B helps correct for the shortcomings of A's naivety. And the way that that works is we connect them up like this with X. But the AB system also has a problem, right? There's some other shortcoming with it that you wouldn't have thought of. So in my new one, I have this be D. Imagine that that's a D. So we try D, and we connect it up, whatever. But the problem is that D actually interferes with B. So this doesn't work at all. So instead of D, we're going to use C. And if we connect up C in this way to A, which is Y, then we can connect it up with Z. And the clever thing about Z is it gets around this problem that D had where C interfered with B. So now we have an entire system. And this all works. And it solves all of the problems. It gets around the issues. And this is great. That was, I hope you will agree, a much more engaging way to build up this concept in people's minds. I feel as though I brought a fair number of people with me on that, despite the fact that this is completely contentless. There's nothing here. And yet, it's a story. It's a contentless story, but it still holds people's attention way better. So the advantages of this are manifold. Firstly, it's more interesting. Secondly, you actually end up with a better understanding, because you don't just know what the parts are, you know why every part is there, and you know why it wasn't something else that it could have been, and what would happen if it was absent. You have much more complicated and nuanced models of the structure of the problem, because you've been talked through the creation of the thing. So that's much better. This is like a second example, which I'm not sure that I necessarily have time for. I'll do it very quickly. It's the same kind of thing. It's a thing I wish my mathematics teachers would do. They would just be like, oh, we want to find the area under this curve. Why? Do we care about that? Whatever. So first off, label your axes, have some reason to care. Perhaps this is like a vehicle, and this is its speed, and we want to know how far it's traveled, something like that. We want this area. So do something like linear interpolation, right? We know how to do this. The maths is easy. But it sucks. Like, there's this enormous error. So we do something piecewise linear. We divide it up into these, 4 segments. And then, again, the maths, we can do it. But there's still an error. So we make our segments shorter. But, 1, there's still an error. And 2, this is more work. And if we want to reduce this error arbitrarily small, we need to do arbitrarily large amounts of work. So calculus. I'm not going to do the whole thing. My point is just you can motivate things with this type of story. There's a problem, there's a solution. You don't literally have to alternate so and but, by the way. It's just make sure you never have just an and then. Another type of story you can tell is adversarial fiction. This is not as widely applicable as the other ones in a technical context. But if you are doing information security or security, cryptography, containment, that kind of thing, that's a useful way to do it. So people also need to understand your work. You've got people to follow it. Telling a story helps, but yeah, the main way that you get people to really understand your work is to aim low. If you aim at the target, it's smooth. Okay, wrong font, I guess. If you aim at the target, you will hit too high. Aim below the target, and you might hit it. What this means is if you want your work to be understood by researchers, aim at undergraduate level at the highest. If you want PhD students to understand your work, aim at high school. If you want government policymakers to understand your work, aim at sort of 8 to 12 years old. And this is not, but this is different from disrespecting your audience. Respect your audience. Do not assume your audience is stupid. Assume that they're ignorant. Right? Don't assume that a government policymaker will know anything technical that you learn after you're 12 years old. But that doesn't mean, don't be insulting. Assume you're talking to a smart 12-year-old. But the point of this is that it forces you to lean on as few dependencies as you can get away with. You probably don't need to import the whole of linear algebra to explain your thing. Can you get away with explaining it with less? If you can, you should. Now, a lot of people would then think, hang on, if I explain my thing simply, won't people think that my thing is simple? To this I say, get over yourself. Forget about being respectable, be clear. People will respect you if you do good work. People will know your work is good if they can understand it, right? If a clear understanding of your work would cause people to respect it less, do better work. So you should write how you talk. You should be as informal as you can get away with. People already know how to explain their ideas. The number of times when I read a paper and I don't really understand it, and I talk to the person, and they say, oh, well, the way to think about that is blah, and they introduce some metaphor or something that wasn't in the paper. I used to have, I mean, I should have on this slide, stop hitting yourself. The number of people who are quite capable of explaining their idea, and then as soon as they get on stage or they start writing something, they become incredibly formal and they just lose the ability to express anything. Just write how you talk. One way to do this is to make sure you read what you write. Read what you write out loud. Things which are uncomfortable to say out loud are also uncomfortable to read. And making sure that your thing flows nicely is important. And finally, explain your thing to real people. Find a person who's a good proxy of your intended audience, get them in a room with a whiteboard, and explain your thing to them. And make notes, or better yet, record and then listen to it later and make notes. And pay attention to questions people have, misconceptions, when people misunderstand you, how and why, and how can you avoid that next time. And also, anytime you find yourself wanting to write some kind of diagram on the board, that should be a diagram, that should be a figure. And okay, that sounds like a lot of work, maybe, and it is, but on the margin, this will improve your work more than spending that same amount of time trying to do slightly better research, probably. So yeah, just to sum up the key takeaways. Communication is the whole point of research. This is extremely important and should be prioritized. Allocate resources appropriately. Put your stuff out there in a bunch of different formats. Make sure people have reasons to care. Tell a story, an interesting story, and the way that you do that is so and but, and never just then. Aim low in knowledge, but not intelligence. And practice explaining your thing to real people. In general, in research, communication is badly neglected. There's a lot of low-hanging fruit. You, I think, have a duty to do better, and it's actually not that hard. You can do a lot better, and you should. You just have to allocate actual time and energy to communication. Thank you.
All right. Thank you, Rob. Very sorry about the slides. Don't know what happened there. Any questions from the audience? Yes, on the far right.
Thank you. I really enjoyed your talk. I want you to put your story into the context of AI safety and AGI safety, because I have a feeling that many people have very strong prior about how dangerous AI is, and particularly in Japan, I have difficulty in conveying this type of problem. And so have you ever stumbled upon this kind of thing in AI safety in particular, and any thoughts about that?
I'm not certain that I understand the question. Have I come across?
Come across that the story of like efficacy of AI safety research to people who don't believe that such research is necessary, or
Yeah, I think that there are sort of competing narratives, right? A lot of people already have a story in their mind of how these things are going to go, and so they're not willing to hear yours because it's contradictory to that. And that is kind of unavoidable, I think. You just want your story to be more compelling. And you know, for different people, there are different things that work there, but fundamentally, you need to tell a story that makes sense, that stands up under close scrutiny. And I guess there is also a thing that doesn't tie in with this, which is poking holes in the story that they have, right? But okay, so one example of a story that could work there is the story of a person changing their mind. If you did believe something different, and you then came to hold the beliefs you have now, what was the process by which that happened? And recounting that story may also walk somebody through the same experience. But that has to be personal. Because if you can't fake that. I mean, you can't really fake anything. People are pretty good at spotting if you're not being honest with them. So yeah, there's limitations to being able to deploy that kind of thing honestly, but if you can, you should, yeah.
Okay,
thank you
we have time for
thoughtful comments. Thank you.
Maybe one more from the far left of the room in the yellow jacket.
Sorry, not a question, but more a public service announcement that about 80% of Rob Miles' videos have Japanese subtitles, so please check them out if you are interested. Thank you.
Nice.
In that case, we have time for one more question, or several public service announcements. Let's go back to the right-hand side of the room.
Thank you. Yeah, I think you're absolutely right. We, as researchers, we need to focus more on communication. And but I think one thing I wonder about is where do you stop? Like, if you've got a piece of research, you don't know whether it's good or not. You don't know whether people are going to be interested in it or not. And you can sink a lot of time and a lot of effort into pieces of research that may or may not be valuable to the community.
Yeah.
I suppose, do you have a sense of at what point should you, how far should you pursue communication?
So you stop allocating resources to communication when you think that a marginal additional unit of resources would be better allocated to research. This was kind of what I was hinting at before, saying that, like, do you think it's easier to double your research quality or to double your communication? There will come a point where, you hit diminishing returns on everything. And so there will come a point where one edge is ahead. I'm just gesturing at that I think most people are not at that point, and probably not close to that point. But it does happen eventually. A lot of the things that I'm saying about ways to do communication well, I actually had an additional slide for this in the new slides, is that the best communication strategies only really work if your work is good. So for example, be excited and enthusiastic about your work. Because if you don't seem excited by your work, how can you expect anyone else to be? You're the person who understands it best, right? So if you find it hard to be excited about your work, maybe you shouldn't be prioritizing communication. Maybe you should be doing better work. In the same way, if you are, if you're explaining things very clearly and concisely and simply, that strategy only works if the thing you're explaining is actually really good, right? If the thing is not that good, it's actually not in your best interest to communicate it clearly, because if people really understand your work, then they might have valid criticisms of it. And that can be very scary. If you just communicate unclearly, you can hide your mediocrity behind a bunch of Greek symbols, and then people won't understand it. They may criticize it, and you can just tell yourself, well, they didn't understand it. And then you never have to improve your ideas. So the communication side of things can help you to do better research, but by making you notice, right? If you're required to use communication techniques that work best when you have good research, that forces you to notice the problems with your research. And this is also not a coincidence. The reason why these communication techniques work well is because they work best with good research, right? People observe oh, this person is very straightforward and to the point. They're not trying to bamboozle me. Probably their ideas are actually good because they don't have to hide behind things, right? This person seems very enthusiastic about their work. It's hard to fake that. So probably they really are excited about it, which is like a signal that it's actually good. There's a lot of synergy between the two sides of things.
Okay. On that note, thank you very much, Rob.
Thank you very much.
Cool. And I would like to start off our afternoon of mechanistic interpretability by inviting Hoagy Cunningham to the stage.
So thanks, Blaine, and also thank you, Noeon Research, for sponsoring this. My name is Hoagy Cunningham. I am currently a researcher at Anthropic. I'm mostly going to be presenting research from last year that I did with my collaborators at Eleuther.ai, and that Anthropic did some very similar work on, which I'm now have joined them to work on. And this is finding features in large language models with sparse autoencoders. But before I sort of get into the meat of what that means, I just wanted to take a bit of time to kind of get a bit of a sense of what this field is, because we've been seeing a lot of much more theoretical work. Now we're going to have a few different talks on interpretability. So yeah, I mean, what is interpretability? There is, I mean, it's a pretty huge field of work. Someone recently said to me that interpretability is kind of the science of trying to understand how models generalize. So we know that we're only ever, with any system, going to be able to observe some finite, limited number of cases where this model is acting, and we want to know how to generalize. We want to be able to predict what it's going to do in these other situations. And I think almost everything can be kind of cast as a lot of things can be cast as interpretability. So when we do evaluations, when we try and evaluate how smart a model is, we're getting a sense of how smart that model is going to be in other situations. So we're understanding its generalization. I mean, other things you can go in more detail. You can sort of, for a given output, you can look at the Shapley value of the tokens and sort of get a sense of which tokens have caused the output. And you can even do things just like playing around with the model, trying to understand the contours of the character of the model. And this, I think, is still interpretability, because you are just improving your ability to predict what this model would do just by you predict a person by interacting with them. Nonetheless, I think, especially because these models are particularly new and weird things, and they're going to be changing a lot over time, we can't just sort of rely on just talking to these things. And there are also lots of situations that we wouldn't want to put them in to even test what they would do. So to get a deeper understanding, we turn to mechanistic interpretability, which is the sort of project of trying to look inside the box. So we have this algorithm, we have this machine learning algorithm, and we know exactly what the code is that it's written on, and we even know exactly what all the parameters are, and we know what all of the vectors inside the model are. Surely we can understand this. It's a very similar project to neuroscience, but it has the advantage that you can run pretty much any test you could possibly think of. You get to start with the exact values of every single parameter, rather than that being a gigantic multi-decade task to map out all of the parameters in the brain. And again, there's lots of types of mechanistic interpretability. So some people would do things like trying to understand the macro structure. Do we find modularity in models? Or perhaps, for example, in transformers, we find that every unit in a transformer is a residual unit. So you will, in an MLP layer, you will calculate the neurons, and they will feed back, and they will add back to the inputs of that unit, and the same for the attention. And so you can see it as consistently updating a single vector, which is getting updated at every single layer. And it turns out you can do things like, just try and take a middle layer and immediately go to the output. And that works pretty well. And so you find that it's a machine which iteratively calculates its outputs in this sort of step-by-step way, which didn't have to be the case. And so you can find some interesting things at the macro level, but what we're really trying to do is more like finding atoms. We want to know what is the sort of core unit of thought that these networks are working with. And, well, one thing you might think is a good idea for these core units is the neurons themselves. They are a neural network. If you're a neuroscientist, you might immediately think this is perhaps not the unit to work with. But to give a very brief history of mechanistic interpretability, lots of the original work was done by Chris Oler and others at Google Brain, and then OpenAI and Anthropic, and Camerata and others. And lots of that work was done using neurons as the unit of analysis in vision models. And so what we have here is like a description of the kind of like the dream of this working. And this is a real example. What we have here is these are 3 neurons in a previous layer on the left and a neuron in the subsequent layer on the right. And for each of these neurons, we can work out like what kind of images would this neuron try to fire on. And you find something that looks a bit like windows and a bit like car bodies and a bit like wheels. And on the next layer, we find something that looks a bit like cars. And we look at the weights that connect up these things, and we find it's looking for this windows in the top and wheels at the bottom, and this, seems to detect cars. So this is like a really nice example of a clean, crisp story we can tell using neurons as the unit to say, well, how is this model detecting cars? Well, it detects them like this. And obviously, there's more to the story. But that's a pretty good starting point. Unfortunately, when they moved from working with these vision models to transformers, and especially to language models, we find that the neurons just don't seem to work as well. So in the way that we found that these neurons would consistently activate on quite like clustered examples of things. When we look at when this neuron is active, we can understand the kind of semantic cluster. We immediately have a reasonable guess of what kinds of things will activate this neuron. When we go to language models, this is much less the case. There's maybe multiple clusters. Sometimes it just doesn't seem to make sense at all. And so there's this question of, well, why would it be the case that in a vision model, neurons seem to mean specific single things, and in a language model, they just don't seem to mean specific things in the same way? And again, in my very stylized history of Mech and Tup, the second paper is on toy models of superposition, which is an investigation of when you would expect to see this phenomenon using lots of like simple, small examples. And what we see here is we're going to say, well, let's imagine that there are some larger number of features. Maybe there's 100 features, and we're going to try and compress those down into maybe a 10-dimensional layer, a 10-dimensional space. And we're going to say, well, how does it do that? Does it actually manage to represent all 100? Does it even try to represent all of 100 features? Or does it say just pick the 10 most important features and give them all a neuron and we just ignore the rest? And the kind of determining property that they found was whether or not it gives a single feature to a single neuron depends on how sparse those features are. And so what we see here, this is one of their examples. Each column here represents a single neuron, and the sort of little units, sorry, it's not very clear on the screen, but these yellow ones are made up of lots of small little blocks. And what that's saying is that in the top case, this is when the sparsity is 0, so all features are on all the time. What does it do? Well, each neuron just represents a single concept, and if there are any more concepts than there are neurons, we just won't represent them at all. In this other case, we have sparsity is 0.999. So what happens in this case? Well, because these features are so sparse, it becomes advantageous to the model for each neuron to try and represent multiple concepts, and each concept will be spread across multiple neurons. So there's this kind of, this key relationship. We have low sparsity, we have features being on often or even all the time, then they will expect to get a dedicated dimension, perhaps a dedicated neuron, and when the features are really sparse, we'll move to this sort of distributed representations or superposition case where neurons represent multiple different things and the kind of units are spread across multiple neurons. Okay, so given that we have this sort of basic picture in mind, how should we kind of recover it? If we don't want to use neurons as the basis, what should we do? Well, as we've just said, we have this belief that we are now in a model where we have way more features than there are neurons, than there are dimensions in any given activation space. But we also believe that these are sparse. And this makes a lot of sense if you think of what's going on in a language model. I mean, if you think with a vision model, you might have textures and shapes and colors. These things are very common. They exist in sort of most images. When we think about concepts, maybe like people or even just particular words, types of verbs, they're going to be very rare. And so very few of these features will be active at any one time. And so we can convert this almost directly now into a sort of neural network architecture of our own. So we can take our activation vectors, whether this is from an MLP or from the residual, which is where it's added back into the input, we can take that vector and then we can try and say, well, if we had really knew what the features were, what should we be able to do? Well, we should be able to expand this vector out to a much wider space where each of the dimensions are these new features, but that this wider space should be very sparse. There should be very few of them on, much fewer than the dimension even of the much sort of thinner activation layer. And then we should, because this is kind of all of the information, we should be able to reconstruct the original activation vector from this wider sparse space. So that's the kind of intuition. And we cache this out as a very simple machine learning problem, which is to say, we have X is our input. Our features are a ReLU of just a matrix plus a vector. We reconstruct them with another matrix. And that matrix can also be thought of as a sum of feature vectors. And then the loss we apply is a mean squared error loss, so we want to be able to reconstruct it. We have an L1 penalty, so this is where the sparsity comes from. An L1 penalty says we're just going to add up all the activations. So if we have two features on, one is on with a magnitude of 5 and one is on with a magnitude of 2, the L1 loss will be 7. And this is a little bit funny because L1 is not really what we care about. What we really care about is just the absolute number of features. But this does not have a good gradient. This is like a very difficult thing to optimize. And there's like a load of research which shows that using L1, optimizing L1 is a sufficiently good proxy that you will recover L0, like properly sparse solutions. So yeah, we use the L1 penalty. This is where the sparsity penalty is applied. And yeah, we can just train this. We can take millions or billions of activations. We'll take a language model, we'll just get a big data set and we'll run the model on it and then pull out these vectors in a particular layer. It can work on any layer, or maybe not attention. Attention needs some extra work. But on MLP and residual layers, we run it through this model, and then we're just going to see what we get out. And we get out a lot of things, and the question is, how do we even start looking at that? And the kind of basic thing you can do is to say, well, okay, now we've got one feature. We've got one dimension in this wider space. What are the cases in which this feature is most active? And so this is from the Anthropic paper, their one-layer paper, and we can see on the left that these, it seems to be activating most strongly on nouns at the end of the word, at the end of noun phrases. There's like a fair amount of clustering in terms of game and station and warehouse. It's not like a perfectly clear unit that we immediately make sense, but it seems to be like quite sort of consistent and clustered. And this is the kind of thing that we see. And as you go to larger models, you start to see much more interesting things. This is not like, in a one-layer model, you're not going to expect to see brilliant structure, but it seems, it's not like a combination of obviously separate things. Now, obviously, just looking at the top activations isn't going to tell you a huge amount. Even in cases like neurons, just looking at the very top activations often looks very clustered. Even when you sort of, dig down into this dimension, there's like lots of other things going on. So we can kind of have a look at that. This is a feature which seems to fire on Arabic text. And so this is a histogram. The x-axis is how much the feature has fired. And this is a histogram of the amount of times that is fired this much. And the red is Arabic text, and the blue is probably not Arabic text. And we can see, interestingly, firstly, that it's not like anything, it's nothing like a Gaussian distribution. We have this big lump. This is, suggesting that we found some kind of just structure, at least. And then we can see that it's quite clearly separating out Arabic text, not just at the very top, but throughout its range. And then we seem to cut off the feature roughly when, it's mostly turning off Arabic, going back to normal text. And there's probably some cases of Arabic text which it doesn't catch, but it seems to be pretty good. So that's a sense of one good feature, perhaps. But we can then use that to say, well, let's understand a passage of text through the eyes of this autoencoder. So this is John Keats's Ode on a Grecian Urn, I think. And what we've done here, we'll run the autoencoder over this whole passage. And I've highlighted the word earth here, and we're going to see which kind of clusters seem to be active at this particular moment. So, and the coloring here is the proportion of the maximum activation. Of all of the activations we've seen, what proportion do we have at this word? So the highest one is early modern Shakespearean English. So firing on things like words which contain things like thee and ye. And so that's not on this word in particular, but just previously and in the paragraph. So it's tracking as a whole the fact that this is in this very early modern English. We have the second one is labeled sun and says things like celestial bodies. So obviously Earth is a celestial body. And then as we go down, things which are sort of somewhat related, but maybe less exactly clustered, things like grass and farm related concepts, descriptions of nature. So we can get a sense of like what kind of clusters the model is kind of treating this input as containing. And again, this is an interesting window into a one-layer model, but it suggests that perhaps for much larger models, we might be able to get some much richer kind of insight into what's really going on there. I mean, one problem you might have with having larger models is, like, we might find millions of features, we might find tens of hundreds or billions of features. How could we even look at them all? And that's where I think it's a kind of research where we can leverage large language models a lot to like really help us get a hold of these features. So one thing we can do is, and this is following some work that OpenAI did last year, you can say, okay, here's a feature that we've learned. Let's see loads of examples of when this feature was active. Can we then feed that to a language model and get it to give a guess of say a few sentences about when we think this feature is active? And then not only can we get it to sort of describe the feature, but we can test its description, because then we can separately give another language model, just the description and say, predict when will this thing activate? And we can like judge it. We can judge the quality of the feature based on the degree of correlation between the predicted and the actual activations. And so this allows us both to like maybe feel confident that we can actually get a grasp on potentially tens or hundreds of millions of features. And it also allows us maybe, if our protocol is good enough, which I think we haven't demonstrated yet, and we're working on this internally at Anthropic to make these things better, but yeah, to maybe get a judge of like, okay, how good was this sparse autoencoder versus that sparse autoencoder? So I think there's a lot of promise in this kind of, really bringing in the language models to help understand the language models. But kind of stepping back a little bit, I also want to talk about just, like, why do we think that we've sort of found something kind of real here? I mean, there's always a danger that we find something that's sort of a cluster. It's an interesting fact about the model, but are we finding something which is kind of fundamental to its computation? And I think this is something this is hard to answer, and I don't think we've necessarily answered it totally. But I wanted to go back to this Arabic feature, and instead, on this histogram, what we have is instead of the context in which it activates, what we have is when this feature is active. This is just a one-layer model. So when this feature is active, which tokens are most up-weighted by this direction? So, this feature is active. We can just multiply through the matrices and ask, well, when is this going to be, what direction does this push the model in terms of its answers? And right on the far right, forming a separate peak, that is the tokens which correspond to letters in Arabic. And they're really quite nicely separated from the other ones. So we're finding that not only is this firing on Arabic, it's not just finding that it is Arabic text, but it's acting to upweight the probability of the subsequent text being Arabic. And not only that, but there is no neuron that we could draw this graph for. You could look over any number of neurons. We could look through every single neuron, and there is not any neuron which separates these out nearly as cleanly, not in terms of the logic weights, and not in terms of the being able to just detect the Arabic. So I think that's an indication that we are really separating out not just what's in the space, not just the information in the space, but what the model is actually doing to act. How is the model doing computation? I think there's a lot more to answer in that case, but I think this is just one indication that we are at least pointing towards something which is kind of true and important about the model. In terms of how we would go further, obviously this is just finding a sort of cluster in the model. So we might say, haha, we've found a feature in the model which is active if a person is lying. Now we might care about that. We might think if the model is thinking that it's lying itself, that would be interesting. But what we really want to know is how is the model going to act on these features, and how is it going to sort of build them up over time? And this is still definitely a work in progress. And in fact, there's been some really interesting work really developing this in the last week, which I haven't had time to look at, by Sam Marks. But this is from our paper. This was our kind of initial version of looking at this. and we'd find this was on a 6-layer model. We'd find in the last layer there was a feature which would particularly make it likely that a closed bracket would be predicted. So, okay, we're going to predict a closed bracket. Well, which features cause this? Well, in the middle layers, we find things which are, I'd say at the top we find features which just detect the open bracket, and then we can find that those influence later on in the model, and presumably later on in the token, in the text, we find features that will track whether the open bracket, we are within a bracket, and then later on we realize, okay, now it's time to close the bracket. And so we can't flesh that story out in perfect detail, but we can get a sense of how it builds up the complexity from sort of recognizing inputs to tracking longer term kind of things about the model, and then into converting that into action. So this is just a very early kind of idea of how we might get some more serious statements about what this model is really doing. So that's our kind of basic picture. I think we're learning something really interesting, but there's a lot to do. So this is just a set of things that what we're going to try and do next. So like I was just saying, we want to do circuits, and there's been some great work of that literally this week. There's a lot of really, really fun things coming out from various different labs and independent people on this kind of work now. We also just want to train these things better. We want to train them to huge models, and we want to get the right hyperparameters. And there may be many tricks and tweaks, and maybe it's not even the exact right kind of formula for training. We also don't really know if we can apply these ideas to attention properly. And interestingly, we still have I don't think the perfect understanding of what we are finding. So one thing, early on we said that there's, in the vision models, there is something which really pushes features to be concentrated in single neurons. And we would expect there to be still some kind of pressure, even in language models. They might not be on a single neuron, but they might be on 10 or 20, not all neurons. Whereas what we actually tend to find in these layers is something which is totally spread out. So I think that's just one maybe pointer towards the fact that we don't have a perfect understanding of what we're finding here. So yeah, lots of future work to be done, scaling and training. It's kind of time for questions. I've given some pre-Q&A questions for just sort of general things that I didn't really cover. The first one is this assumes that everything is linear. If a feature is not linear, it won't be picked up by this model. Is this not a dangerous assumption? And I think Oskar is talking about linear representations immediately. I would just say there's been a lot of interesting work from Oskar and others, showing just how many rich things can be represented linearly, not just features in the sort of classic sense, but even tasks. When we ask a model to do something, the nature of that ask can even be represented linearly. And what have we really learned about the model? We're grouping these things together. We definitely need circuits. And when do we think this might help? I think there's lots of cases. I think we might just learn more about the model because it's just such a mystery. It's such an open door at the moment. I think especially perhaps it would be really good. Companies are starting to offer fine-tuned versions of models, and we want to have a really quick way of understanding what changes are made when you fine-tune a model. And I think this maybe can provide an answer of actually what has been changed in the model when we've just given it these few examples. As well as, I think if these really are the atoms, I think there's almost an unlimited number of things we can do. So I think it's a really exciting thing. Anyway, those were my quick questions, but your questions.
Let's bring the lights up. Yes, straight away from the front and center.
Yeah, thank you for the nice talk. So you're essentially trying to decode these features which you assume are sparse, which are then somehow stacked through the superposition in the real model, or in the trained model then. It would be interesting to hear your thoughts on the choice of sparse autoencoder, and especially the size of the middle layer, and what happens if you have too large one, or when it's too small. And if you could comment on that failure modes in either case.
Yeah, so this is a really great question. I think what we kind of hoped to find initially was something that I could have covered here, which was, we were hoped that there would be a discrete number of features. So if it was too many, maybe things would go wrong, or maybe they would just never turn on. That would be the sort of easiest version, and maybe if there were too few, I don't know, it wouldn't quite work properly and somehow. I think what we find instead is that it's much more smooth. We make it as wide as you want, and sometimes these things, because of the sparseness, it's quite easy for features to die. because they'd get to a region where they just never have a gradient. But assuming they haven't actually died, which is more of a training failure mode, it seems like it just continually finds like more and more and more fine-grained distinctions, which is, I think, maybe an evidence that it's not quite, although we are finding something about the clustering of the model, it's not the sort of perfectly discrete set of features that we might have hoped.
Cool. Could you pass the microphone back and to your right to Kai?
Hello. Hi. So if we want to do mechanistic interpretability on multimodal models, so say it's taking audio, vision, text as input, do you expect you'd want to be using different methods based on, say, the layer or depth you're looking at, or would it be more based on the natural distribution of properties in the data, like, as you said, like spatial vision, natural images contain different distributions to text data, and then finally, if you had a sort of multimodal space towards the end of the model, like what sort of methods would you be using to something that's integrating like information from all of these different modalities?
Interesting question. I mean, I guess with vision models, we've seen that, like, especially in the early layers, like just looking at the neurons seems to be pretty good. I think there's some really interesting work that hasn't yet been done, which I would love someone to do, which is to compare, like, at what point does it seem is there a crossover, or how well does sparse autoencoders work in this kind of early vision sense? When it comes to audio, Eleanor Reed did some interesting work on the audio models and like found that you could like find syllables quite nicely in the residual stream in a way that you couldn't necessarily discover otherwise. So I think these things seem promising for at least the inputs. I think, like I alluded to, I think theoretically it seems like we should want to adjust perhaps something about the way we're doing for the sort of statistics of the neurons and how sparse they are, and I don't think we necessarily know how to do that. So I think there may be some adjustments to the kind of techniques that we would make if we knew how. But I think at the moment, like, this does seem to be the kind of best technique that I know of, at least, regardless of model layer or depth.
Okay, I think that is sadly. I think we could do one more. We can do one more. If you head to the.
Hi, thank you. This is a follow-up to the previous question. Have you tried things like checking the goodness of fit, where you are doing the encoding and then the de-encoding? You're basically, and then you check how well you've been able to decode the original thing that you encoded.
How well does that work, basically?
How well does that work?
Yeah, great question. It really, really depends on the model. I think with their one-layer models, which have some kind of advantages because there's kind of a natural sparsity that's induced by just the fact that the tokens are just there, and generally in early layers, you can really get it down pretty well. I think the measure we often use is not exactly like, well, you can say sort of proportion of variance recovered or something. What we often do is like, if we like ran the model forward, but using our layer instead of the actual layer, or like going through our layer as well, like what's the loss? How much do we lose in terms of model capability relative to just having taken out that model, taken out that layer entirely? And for this one layer model, you can get up to like 95, maybe even higher percentages. For the like middle layer in a sizable model, generally at the moment we're looking more in the kind of 80-90 range, 80-90%. So there's definitely some somewhat sizable losses, but it's a pretty large chunk of.
Because I guess that can help you address how wide you need to make the internal layer.
I mean, it's definitely a good point that we would love to. I mean, ideally, there would be a point we could sort of draw this line, and they'd be like, oh, maybe this is how many we need for perfect reconstruction. At the moment, it's kind of like more of it sort of flattens out, and often it flattens out, quite aggressively, where like going from like 1 million to 2 million features doesn't necessarily give you that much. And one of the big questions that I'm working on at the moment is like, okay, given we're doing that kind of work, is that because we just aren't good at optimizing it, or is that something fundamental? And that's quite hard to figure out.
Thank you.
Okay, thank you, Sam. And thank you, Hoagy.
Thank you, Blaine. Thank you.
Great talk. And I'd now like to welcome Oskar.
Hi everyone, I'm Oskar. I'm going to talk about the work that I did during my MATS fellowship program. You heard about that program from Ryan yesterday. I'm very grateful to them for setting me up with my wonderful collaborators, in particular my primary co-author, Kurt Tiggs, and our two mentors during the program, Atticus Geiger and Neil Nanda. The work that we did was in the field of mechanistic interpretability, in the same sort of area that you've just heard from Hoagy. Perhaps to categorize the difference, we were taking more of a bottom-up approach to finding features rather than a top-down, because we were interested in a specific feature of interest a priori, which is sentiment. Text sentiment is perhaps one of the most ubiquitous and obvious and natural features that you would want to find or study in text. And we wanted to see, yes, could we find some representation of this feature within a language model? So the way that we began this was we took about the most simple data set that we could imagine, which was a set of prompts of movie reviews, which we hoped would induce the model to tell us what it believed was the sentiment of that movie review, using the language model's natural ability to predict the next token based on the way that we structured those prompts. So this was a data set of prompts where they only had two valence tokens. There was an adjective and a verb, which are natural ways of expressing sentiment. So within the data set, those were the only two token positions that were varying. And we looked at the residual stream. So you've heard Hoagy talk about the residual stream. It's basically the working memory of a transformer model. At every token position, it can only read and write from the residual stream, and the residual stream at the final layer via the unembedding basically determines the prediction of the next token at that position. So it's a natural place to go looking for features, and the first thing that we did was we visualized, using principal component analysis in 2 dimensions, what the space of these residual streams at those tokens looked like. And pleasingly, we found that they were naturally clustered, as you might expect. And when you zoomed in on each of these corresponding clusters, you indeed found that on one cluster it was all of the positive words, whereas on the other cluster it was all of the negative words. So it seemed to us, from this very basic initial exploration, that there was some structure within the language model's representations that encoded sentiment. A lot more to be discovered at this point, but it suggests that we could attempt at least to go looking for a representation. And based on this 2-dimensional principal component analysis, and also lots of theoretical reasons within the literature why we think representations of features should be linear, we decided to go looking for a single direction that would hopefully represent sentiment. So how did we go finding an actual direction within this large vector space of the residual stream that will hopefully represent sentiment? Well, based on the clustering that we saw earlier, a natural first thing to do would be k-means. With 2 means, you would determine in an unsupervised way 2 clusters with a centroid for each cluster, and then you could draw a line from one centroid to the other that would hopefully correspond to sentiment. We've already talked about principal component analysis, PCA. We saw that in 2 dimensions to observe this clustering, but you could go straight to 1 dimension to determine a single direction that hopefully captures most of the sentiment information in the model. Another very simple and obvious method is just take a positive tokens representation, a negative tokens one, draw a line between them. Do this for all of the examples in your data set. You get a bunch of lines connecting positive to negative. Take the mean over all of those. Another one is to train a classifier or a probe using logistic regression, which will hopefully find a way to separate or split the 2 clusters of positive and negative sentiments. The final method that we used is one of the more modern approaches, and one that I suspect far fewer people will be familiar with, and it's due to one of my co-authors, Atticus Geiger, from a previous work, which is called Distributed Alignment Search, or DAS. So in the same way that you can think of logistic regression as being an optimization-based method, which is trying to find the best possible classifier, from a correlational perspective, the best possible direction, DAS is basically doing the same thing but for causation. we've heard a lot about Judea-Pearl style causal attribution already in this conference. And this is where this idea comes from. The idea is to find the direction which, by some metric of how much it's changing the outputs, which direction is most causally influencing the actual model's outputs. So, with those 5 methods in mind, we can find some directions. And fortunately, to simplify the rest of this talk, what we find is generally, particularly for small models, that you get very high cosine similarity regardless of which of these methods that you use, and exactly which data set that you use and so on. It seems to be relatively robust. It seems like they're hopefully all kind of converging on the same answer. So for the sake of the rest of the talk, you can just assume that we have a sentiment direction computed with one of those methods, but we basically just have one direction that we care about. And the question now is, can we really convince ourselves that we found what we think we found, that we found a single direction, a linear representation of sentiment within a language model? So the first way to test this is this correlational approach, where we're going to run the language model on a set of text from the real world. This was done using open web text from Hugging Face. And at each position, using color, we're going to visualize whether what I'm going to call the sentiment activation, as in, if you take the residual stream and then you project the residual stream onto this direction that we believe is the sentiment direction, you get some number, which is a single floating point number. And so we can visualize that at each position very easily. So blue is corresponding to one side of this axis, and red is corresponding to the other side of the axis. And indeed, what we find, if you look at the words that light up blue, they look like they are very positive, sentiment-y kind of words that we would expect. And similarly, red ends up being very negative. So you can see those in A, B, and C there. That's done using GPT-2 small. We also did this analysis with some slightly larger models that can do a bit of other languages, which was interesting, because we trained these directions exclusively on this toy data set that I explained at the start, using simple English adjectives only. And not only did it seem to extend to verbs and adverbs and nouns and so on, but it even extended into French. When we put the opening paragraph of Harry Potter in French through the model, the sentiment activations that came out seemed to make sense. It was picking up words like perfectly and good as being positive sentiment, and vice versa for negative words. So at this sort of qualitative level, it looks like on a real-world data set, these directions are coming up as meaningful and seem to do what we think they're doing. But to make that more quantitative, what we did was we binned the sentiment activations, and we sampled for a bunch of times from each bin, and we submitted those words and the context of that word from open web text into GPT-4 as our sort of oracle or our ground truth labeler. So GPT-4 had the final say of whether this was genuinely a positive sentiment or negative sentiment word or not. And what we found was, when we took a word from the left-hand side of the x-axis here, so very negative sentiment activations according to our small model like GPT-2, and we submitted those to GPT-4, we found that in the red area here, the vast majority of those were indeed labeled as negative by GPT-4. Basically nothing is positive and a tiny bit labeled as neutral sentiment. And similarly on the other side of the x-axis, we find yes, in the tails of the sentiment activation, GPT-4 is saying yes, these are very negative versus very positive sentiment words. So at a correlational level, it seems like, yes, we found this direction, and when you look at this sentiment activation, this single number that we've taken from the residual stream space, it seems to pick out positive versus negative sentiment. But the question remains, again, we have lots of fans of Judea-Pearl style causal attribution here. Is this actually how the model is completing sentiment-driven tasks? Is this actually how the model knows to predict a positive or negative next word within the movie review? That remains to be shown. So to do that, we used a technique called activation patching. So this is a technique originally from causal attribution analysis and sort of become very popular within mechanistic interpretability. The idea is that you have two different prompts, each with their own forward pass. And what you do is, as you go through the forward pass of one prompt, you patch or substitute in an activation from the other prompt. So what this looks like in our case particularly, where we really are caring about sentiment, is we have a positive sentiment prompt and a negative sentiment prompt. And as we go through the forward pass for, let's say, the positive sentiment prompt, we patch in just the sentiment activation, so just that single direction in the residual stream space from the other prompt. And then we look at the outputs and see, was this sufficient, this single externally driven change, was that sufficient to change the model's outputs, to switch it from a positive prediction for the next token to a negative one? So there were two different quantitative metrics that we used for this. One was the logic difference metric. So the idea is that to get a sense of whether the model is predicting a positive next token, we would take an example positive next token like great and a negative token like terrible. We would look at the output logics for those two, take the difference between them, and that gives you a sense of whether the model is predicting a positive or negative next token. So you can check what that number is for a positive prompt and for a negative prompt. And then when we do this patching experiment, we'll presumably get a logic difference somewhere in between the two. And we can therefore create this normalized, kind of smooth measure of the logic difference from the results of our activation patching experiment. As well as that metric, we also use the logic flip metric, which is basically a discrete version of the same metric. It's simply a 0 or 1. Did we successfully flip from more likely to be positive to more likely to be negative for the completion? So, what did we find? This is our toy data set of movie reviews that I explained at the start. What we found was we basically could completely flip the prediction. 100% here means we've completely gone from negative to positive or vice versa. Whether you looked at logic difference or logic flipping, basically 100% of the prompts we flipped the prediction. So it seems like this single direction residual stream space was indeed sufficient to be causal within those prompts, even out of sample. At least using DAS. So DAS is what we expect to do the best here, because as I explained at the start, DAS is the direction finding method which is specifically optimizing for being causal. So when we look at the results of these causal interventions, we expect it to show up at the top here. We got good results for many other directions, but that was always at the top. So that's a neat result, but does this apply in the real world? That was just a toy data set that we constructed that was useful so that we could compare across a variety of model sizes which might not be able to handle classification of long movie reviews. So for that, we used Stanford Sentiment Tree Bank, this very useful data set of human annotated movie reviews from Rotten Tomatoes, which has individual clauses labeled as being positive or negative. So we had this big data set of lots of genuine movie reviews, and we could feed that into the model to see whether it predicted positive or negative completions. And so using the directions that we had trained on this tiny toy data set of English adjectives, and then evaluating that using this activation patching experiment, we found that we could flip more than 50% of the predictions from positive to negative using this patching, which is a remarkable example of how a toy data set can give you remarkable insight to predict in the real world. We did a second verification of the causal efficacy of these directions, which I want to share with you. So instead of using activation patching, this experiment was using activation steering. So it's a similar idea, but instead of taking sentiment activations from actual values from a positive and a negative prompt, we instead just said, okay, sentiment activation, that's just a number. Let's add a very positive or negative number to it and see what that does to the model's outputs. We then generated a bunch of completions and again fed them to GPT-4 to tell us were those completions positive or negative. And what we found was that when we added a very negative number to the sentiment activation on the left-hand side of the x-axis here, GPT-4 generally labeled those as somewhat negative or negative. and similarly on the positive side of the axis. So the combination of all these experiments convinced us that yes, that this is actually a direction which is not just classifying, containing the information that allows you as a human to come along and split positive versus negative sentiment, but it is actually something that the model is using to determine its predictions. An interesting phenomenon which we also observed in the course of this analysis is something that we called the summarization motif. So what we did was this circuit analysis in GPT-2 small to see how does it accomplish the task exactly, which, you know, GPT-2 small has 12 attention heads in each of 12 layers. What's going on here? How does information get moved around the model between positions in order for it to generate its predictions? What you would probably think naively is, given that, as we said, there were only 2 positions that were different across the prompts and that really contained the information of the sentiment, you would think that basically attention heads would read these positions, write it to the end position, which would determine the final output logics. And indeed, for many of the heads which affect the output logic, this was the case. But there was this second pathway that was not the majority, but was significant enough to be noticeable in GPT-2, which was that there were these other attention heads that read yes from those adjective and verb positions that contained the sentiment information, but then they wrote to the word movie, seemingly this sort of irrelevant token which contained no information. It was constant across all the prompts that we gave it. And then there were these other heads that we called summary readers, which read from that position and wrote to the output logics, which affected the sentiment of the output. So this gave us the intuition that there is like the potential for this sort of placeholder token positions where you can get these bottleneck activations where a load of information gets funneled through a single position that you wouldn't necessarily expect in advance, that the model can write to it and then use that information later, even if it doesn't have any information that's relevant on its own. So in order to test that this actually occurs and is significant, we did some experiments, some more activation patching experiments, this time using Pythia 2.8b. At the time, it was an obvious open source sort of 3 billion parameter model to use. We've since replicated similar findings with Gemma and Koen and other families of models around a similar size. And we gave it another toy data set, this one we call Toy Mood Story, which had descriptions of a character like Jack and whether he loves or hates parties and whether he's in a good mood at the party or not. So again, it's expressing some sort of sentiment. And what we did in this first experiment, 4.1, was the prompt had a clause containing the sentiment information followed by a comma. And in 1.1 here, what we did was we patched the actual clause, the text which actually contained the valenced information, whereas in 1.2, we patched just the commas. Patching the commas in like layer 0 would have 0 effect because the commas are constant between the positive and negative prompts. It's just a comma. But in intermediate layers, if the model chooses to write some information to the comma that it wants to use later, then patching the comma at that layer could affect the output logic significantly. And indeed, when we computed the logic difference metric from before, we found that it didn't matter quite a lot. It was sort of a comparable number whether we patched the commas or the actual phrases themselves, that these were sort of similarly important in contributing to the overall ability of the model to distinguish the sentiment of the character in this story. So we got very, very close to a sort of 1-to-1 ratio here of which was more significant, the clause or the summarization position. So we wanted to know, could we find a way to get it over the top? Were there some conditions under which this ratio would exceed 1? And indeed, we found that when we extended the prompt to be a full sentence rather than just a clause followed by a comma, and we repeated this experiment patching either the clause or the period at the end of that sentence, and then injecting some amount of irrelevant text into the middle of the sentence, we found that as we increased the amount of irrelevant text, this ratio increased. So if you added enough irrelevant text, eventually the model would decide, okay, I'm actually going to rely more on the summary that I wrote at this period than going back all the way to where the original information was, which we find really interesting as, this trend of language models getting longer and longer context lengths and being able to use that context length properly provides a sort of tantalizing glimpse that maybe these effects could become more significant over time. And finally, just to check, these same results do hold up on not just toy data sets, but in the real world. Again, looking at TreeBank. This time we did an ablation experiment. So by ablation here, what I mean is that running the model through all of Stanford Sentiment TreeBank, you get a bunch of different sentiment activations. We can take the mean over all of these sentiment activations to get some kind of neutral sentiment. And then we can replace all of the sentiment activations with just that one number, so it's constant. So we're just sort of erasing all information that the model is storing along the sentiment direction. And what we found that doing that dropped the classification accuracy by 38%. But we found that if we did that same thing, only ablating commas, seemingly something which shouldn't contain any sentiment information, it dropped the accuracy by 18%. So in accuracy terms, again, sort of almost half of the effect was at these summary positions, just at punctuation. So just to summarize the findings and our contribution in this work, what we see as our value here as a case study of a situation where you have a feature of interest. How do you go about using all of the tools that exist out there in the literature for mechanistic interpretability and causal attribution to find a representation of that feature within a language model? And obviously, it would be great in the future to find features that are relevant to safety with similar methods. And the findings that were novel here were that there actually was like a single direction, a linear representation of sentiment that was causal and was sort of robust to different data sets, different ways of fitting the direction. We seem to be converging on a single direction that represented sentiment. And finally, we had this surprising thing that sentiment information isn't just stored at words that are inherently expressing sentiment, but also at these punctuation kind of positions where there isn't any information otherwise, but the model can choose to summarize or store information for later retrieval. Thanks, and I'll take any questions.
Thank you. Questions for... let's go with a new voice from the right-hand side of the room.
It's very interesting about the influence of commas on the sentiment analysis. Japanese language doesn't use commas as much as English. It doesn't have punctuation besides like the final dot. Do you have any idea why commas are so important in English in terms of sentiment analysis? And could you guess what will happen for languages that don't have commas like Japanese?
Yeah, that's a good question. So we've done some work on this after writing this paper. And my intuition at the moment is that it's very important for a language model to sort of remember a lot of context when it gets to something like a comma or a period or a new line, because otherwise, that comma itself doesn't tell you anything. Commas have very little inherent information to them. And so in order for the residual stream at that position to contain all the information that the model needs to make a good prediction of the next token, it sort of needs to have remembered a lot of previous context and written it to that position. So it can be like, oh yeah, I'm in the middle of an English sentence talking about movies. And so I expect that in those kind of situations, you'd find a lot of information being summarized, whereas, if you went to a random word within a sentence, there might be more context from the word itself that would enable you to predict, oh, this is going to be a positive sentiment adjective next. So I think that it's sort of a compensatory mechanism for the fact that at these positions like pronouns and commas and periods, that yeah, it needs to store this extra context. In terms of other languages, I think there's been, since we wrote this paper, there's been some very good work by other authors looking at this. I think it depends a lot on on what the corpus looked like that trained the language model and so on. I think a lot of authors have recently speculated that the model sort of the model often has like particularly GPT-4 say, seems to think in English, and if you ask it in other languages, it kind of has to translate between English and that other language. So yes, I don't know enough about Japanese to make a fully informed guess, but I suspect that what would happen, assuming it was the kind of model that is really thinking in English, is that at positions where there would be a comma in English, then it would store these kind of summaries. But it would be very interesting to see.
Other questions? Let's go with Kai in the middle.
Hi. Do you think that language models that have a sort of proper working memory might have a bit more interpretability in the sense that they could properly summarize things in working memory rather than have to put them in the context because they just have nowhere else to put them? So I guess there might be related work with the sort of vision transformers need registers, where they saw that because vision transformers don't have memory, they put things at weird background pixels in order to compute, and then they gave them working memory, and they put the computation there. So do you think, similarly for language models, this might be a way to get more interpretable representation just because they don't have to shove it into commas and periods and stuff?
Yes, I definitely think that the current paradigm of transformers and the residual stream is somewhat, I want to say, almost say cursed, but challenging for mechanistic interpretability, in that there's just like so many different kinds of features and information that is getting compressed into this relatively small vector space. And yeah, I think if there was more of a natural place for this information to be stored, it would probably be a lot more interpretable. That is the sort of the dream of SAEs, is to, sparse autoencoders, as Hoagy was talking about, to try to fix the mess of the residual stream and recover something which looks a bit more like a working memory. Yeah, I don't know if transformers are here to stay. If they are, SAEs are sort of a backup hope in that direction. Otherwise, yeah, perhaps if RNNs or something else becomes more of the dominant paradigm, I think this could change a lot. And it could well end up being easier for mechanistic interpretability if it did.
Okay. Sadly, that is all we have time for. However, we're about to go into a half-hour coffee break. One last chance to have a look at the posters, schmooze with the speakers, ask any remaining questions you might have. So, thank you very much, Oskar. And I will see you out in the foyer for coffee and a chat. All right. It's time to get back into things. I see once again people are still embedded in conversation out in the hall. Can I ask for Andrei? Could you go out into the hall and do a quick clap, 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 come back in, please? Thank you. I see the swag is slowly disappearing from the conference tables. That's a good sign. The more you take home with you, the less we take home with us. And the more you get to enjoy our beautiful tote bags. I see people slowly filtering in. Come in, take a seat. We're about to get restarted. Last two, possibly best two talks of the day. Not to give you too much to live up to. All right, Andrei has come and sat down, so I assume that everybody is following him. Welcome back to TAIS. Our last two sessions will be Mech-Interp 2. I'd like to welcome Aleksandar Petrov from University of Oxford.
Hello. Thank you for sticking around, and I hope you're well caffeinated for a little bit of math at the afternoon session in the second day. It's usually a tough spot. Hi everyone, I'm Alex. I'm a PhD student at the University of Oxford. I'm in the Tor Vision group. My supervisor is Philip Tor, after whom the group is named. I'm also supervised by Adel Bibi, and that's work that we did together. Well, actually, two works that we did together. Yeah, so quick show of hands. How many of you have done prompting recently? Surprisingly, there's some people that did not raise their hands, which is concerning. But I assume you all have, maybe not recently, but you have experience with that. This is how most people interact with AI systems, language models these days, and it's yeah, how we use them. But there is no surprisingly little about how prompting works and what you can do with them and what you cannot do with it. And when we want to study the capacity or the ability of AI systems, we first usually kind of think about approximation theory, right? So approximation theory is essentially if we have a class of very complicated functions, can we approximate it with a class of simpler functions that we can understand better? So one very classic result in analysis is that the set of all continuous functions on a bounded set can be approximated with the polynomials to an arbitrary degree of accuracy. And polynomials are much more easier to work with. We can analyze them. We can do a lot of interesting stuff with them. So when neural networks started to become a thing, and back then there were many different competing approaches to AI, one of the things that people had to show is that neural networks can be universal approximators for continuous functions. So the first results, I think, came around 1989, so that's 35 years ago. Since then, a lot of different flavors were developed. Then 2006, I believe, we had the first results on universal approximation for RNNs. Then 2019, we had results that transformers are universal approximators. And last year, 2023, Shida Wang from Singapore showed that linear RNNs, or now we call them state space models, they are also universal approximators. So we have all of these results, very rich history. But they all deal with what happens when we train a model, that is when we allow the weight of the model to be perturbed in order for us to approximate a function with this model. But prompting is not that, right? Like prompting is we keep the model fixed and we change the input. And surprisingly little is known about what you can achieve and the scope of functions that you can approximate by prompting a model. So that's what we wanted to actually look at. So attention is going to be something that we're going to talk about because it is the core part of the transformer architecture, which is what powers most of the big models these days. So that's how attention looks like. I hope most of you have seen the equation. Essentially, transformers work over sequences of tokens, and attention is the mechanism through which we combine information from different tokens, and then there's usually element-wise operations that are mixed in between. So here you can see we have two learnable matrices, the query and the key matrix, WK and WK. We multiply our inputs, so the key and the query. So the query is the position at which we care about at the moment, and the keys are all the other positions. We multiply each one of them with the respective matrix. We take the dot product, which measures similarity, and we average this across all of the key positions to essentially have attention that sums to 1 for that particular token. We'll see quite a few variations of this, but fundamentally, that is what powers transformers. Now, we said prompting in context learning, theoretically, they're the exact same thing. They just mean that we prepend some tokens before our input in order to guide the network to do something. Very simple example, if you want to translate English to Japanese, we give the prompt translate English to Japanese, then we give our input, our English sentence. Neural networks are weird, and then the model auto-regressively generates the translation. Neural network wa okashi desu. Right? So everybody hopefully has done this, even the ones that did not raise their hand. We can actually do something slightly better or easier. Tokens are very difficult to optimize automatically because they're discrete. We can't really do gradient descent. So instead of that, we can actually directly optimize for the continuous embeddings right after that. They also have more capacity because continuous vectors rather than discrete set of values. Or we can push, and that's called soft prompting, or we can push this to the extreme and essentially optimize for the inputs of every single attention layer, which is called prefix-tuning. But other than that, it's the exact same idea. It's quite easy to see that prefix-tuning is a superset of soft prompting. So any soft prompt can be represented as a prefix if we just pass the prompt through the model. And similarly, any prompt can be represented as a soft prompt. So because prefix-tuning is the most powerful of these techniques, we'll just focus on that. But you can imagine that anything that we say also applies for prompting. So the first key claim that I'm going to make, and I'll try to justify to you, is that prefix-tuning, and hence prompting, cannot change the attention patterns over the content tokens. So let's look at an example. So this is how the attention looks like. It's the exact same equation that you saw before. And we want to translate with our pre-trained model the sentence neural networks are weird to Japanese. So we want to start to produce the first token in the Japanese translation. So we're looking at the attention of the weird token to all the other tokens. And the pre-trained model attends the most weird, which is weird because it should attend most to neural networks. If you remember, the Japanese translation started with neural network wa. So clearly the pre-trained model is not particularly good at Japanese. Now, if you want to do full fine-tuning, that is, we allow for the model parameters to change, that is, we can update WQ and WK, then obviously we can change the way that attention is computed in any arbitrary way, so we can make sure that the new model, our fine-tuned model, does have the most attention on neural networks, which would be what one would expect. However, if we do prefix-tuning, now remember we don't change the model parameters are exactly the same. The only thing that happens is that we have this prefix s now, and it adds this extra term in the denominator, which is the amount of attention that position I gives, or in our case, the position that has the token weird, gives to the prefix. So if you actually look at the maths, all that the presence of the prefix does is that it lowers down the attention for all of the content tokens. So this is neural networks are weird, these 3 tokens. But it cannot change the relative attention between them. So the absolute values will decrease, but there's no prefix you can put there. There's no s that you can put in there that is going to change the fact that this model attends more to weirds than to neural networks. So that already seems like a very interesting limitation of what you can achieve with prompting and prefix tuning. But as we know, attention is not all that is in a transformer. We do have this extra operation where we combine, where we compute values for each token, so by just multiplying the token value with the value matrix WV, and then we use attention to actually do a weighted average over these positions. So natural question is, okay, how does this kind of limitation of attention follow through to the computation of the activation of the layer? And if you work out the maths, it's quite simple actually. But if you work it out, you end up with the fact that the prefix-tuned activation is simply a linear combination between the pre-trained activation, TI in this case, and a fixed point in the representation space. So that is just WVS, the value of your prompt. or your prefix. And that is all prompting does. All that prompting does is it pushes your activations, the ones of the pre-trained model, towards a fixed point in the representation space. Now, the amount of pushing this capital A to the attention is the amount of attention of that particular token to the prefix, and it can vary between positions, so different tokens can be pushed differently, as you can see in this illustration, towards that point, but they're all pushed towards that fixed point, and that fixed point does not depend on the input. So next time that you use ChatGPT, and you give it like very fancy instructions of what to do, fundamentally, all you're doing is you're just biasing everything towards a point. That raises a very interesting question. Why does it work? Right? Like it's such a it seems like such a restricted action space that your prompt actually can work in. How come this works? We have some experiments that kind of show that seems to be sufficient if you want to specialize the model to a skill that it has seen during pre-training, which is not quite surprising. But also you can kind of use it to learn new skills as long as they're compositional and skills that it has already seen. So if it has seen A and it has seen B, now it can kind of combine them. Like you can find a prompt that will combine these things. But our experiments show that you probably won't be able to learn a completely new task. So if the model has never seen this thing and it can't really combine existing skills for this new task, then it's probably going to fail to find, like, you won't be able to find a prompt that can solve this task. This has two implications. On one hand, it's kind of sad because it means, well, you can't really prompt your way into doing anything. On the upside, for safety, it means that if you did your due diligence and your model doesn't have, let's say, skills to build a nuclear weapon, then the users cannot prompt their way into making it build a nuclear weapon. However, while the first part, so the limitation that all prompting does is just like biasing everything into a fixed point, that's a theoretical result, it holds for any transformer. That is true, absolutely. The second part is intuition and empirical results, and that really didn't sit well with us. But we had two options. One was to just sit around and like hope nobody notices and somebody like actually does the follow-up and maybe analyzes this more formally. The other option is that we actually do it ourselves. So even before that paper got accepted, we already had the follow-up that kind of was saying, well, these empirical results actually don't quite stand up to theory. And this is actually what it turned out. Prefix-tuning can be a universal approximator. So that seems to be a contradiction with what I just said, so I'll kind of resolve this at the end. But let's first look again at the attention equation, right? So it's the exact same thing that we saw before. I have just split the prefix part, so the PIs and the part with the input. We will just consider a single input for the time being. And it looks something like this. It is quite difficult to analyze theoretically, but you can start simplifying stuff. And we'll hope that we can bring back this, like the complexity later. So first thing, notice that the prefix parts, the PIs, they appear twice. Once when we compute the attention, and once when we compute the value. So let's just give us a little bit more freedom, and let's give two different values to both of them. So we have PI alphas for the attention and PI betas for the value computation. Now let's get rid of some terms. The attention of X on X kind of doesn't have anything to do with prompting, so let's just get rid of it. And the numerator is quite complicated to deal with, so let's also get rid of that. And now we're left with this thing, but we can control PI alpha and PI beta, so do we really need these matrices? Not quite, so we can get rid of them. And we're left with this very simple expression, which I'll call core attention. And my claim is that analyzing the approximation properties of this thing, of core attention, essentially tells us what attention hat does. Why? Well, let's look at this thing. If you squint and look hard enough, it starts to look a little bit like a kernel machine, right? So you have these PI alphas that you have the dot product with X, and dot product is a measure of similarity, but it's also a measure of distance if you restrict yourself to the hypersphere. So if we restrict ourselves to the hypersphere, then we have this measure of closeness between X and these control points, PI alpha. Then we have this lambda, which is like a scaling factor. We take the exponent. So this is kind of like weighing function, and then we have these pi betas, which we can think of as the values at these specific control points, and then we average everything. So it kind of looks like a smoothing operation where things that are closer to x matter more. And we can see this in the illustration. So we have 4 prompt positions, like these 4 solid arrows, and our x, the black dotted one. We have this weighing function that's essentially computed by the exponential, like on the left side. Now, as mentioned, pi beta, it kind of governs what the function value should be at this location, so the scale of these vectors. And the smoothing operation essentially gives us the value for x at this particular location. And we can do this over the whole like hypersphere, and that kind of gives us an approximation of a function. Now, lambda actually governs how localized the effect of each control point is. So a larger lambda means that we are effectively approximating a nearest neighbor classifier, but that means that we need larger ends, right? So we need more of these control points, which means more like longer prompts. If lambda is small, then we're doing more smoothing, so we cannot approximate less smooth functions, but on the other hand, we need shorter prompts. But fundamentally, and trust me on this, you can read the math in the paper, but I'm saving you about 8 pages of proofs. This thing's a universal approximator, right? For functions, continuous functions on the hypersphere. Now, if that's the case here, and like kind of you can ignore the hypersphere thing, you can then show that the hypersphere, like the Euclidean space can be mapped to a hypersphere, so that's not really a restriction. But what is a restriction, that this is not an attention head, this is not a transformer, right? Like that's a different function. So let's make our way back up. We can just bring the matrices back. They should just be identities or scaled identities, right? Like to have the exact same thing. There's a trick that we can use to make this term, that with the attention of x on itself, to be 0, so we could also add this term back. There's another trick that we can use to bring the normalization term back. So it turns out that this is almost a constant. Imagine like if you place the control points uniformly over the sphere, then there's always like pretty much the same situation regardless of where your x is. And we can actually bound how far this is from a constant and take this into account. And finally, we can actually put the 2 parts of the prefixes together into single prefixes by just concatenating them and making the input space larger. So using all these tricks, you can formally show that if the core attention is universal approximator, then the attention head is a universal approximator. So the conclusion is, and this is very surprising, at least it was to us, that a single attention head, you don't even need a transformer, a single attention head with a sufficiently long prefix can approximate any continuous function on the hypersphere. Now, this is single input, single output functions, right? We're not talking about sequence to sequence or whole transformers. But we can use this as the building block to show that a transformer can approximate any sequence to sequence function when prompted. And it's surprisingly small transformer. So I'll skip the details, but if you want to model functions from t tokens to t tokens, then you need only t plus 2 attention layers. So that's the depth of the transformer that you need in order to be able to approximate any continuous function from t inputs to t outputs. This is quite interesting. It's linear in the sequence length, and it also does not depend on the precision that you're trying to achieve. So if I want to have better approximation, I don't need a deeper model. I just need a longer prefix, so only my n increases, which is quite unexpected, and it's kind of much better than previous results. So before I showed that prompting and prefix tuning cannot change the attention patterns, and made a claim that probably because of this we cannot learn new tasks, but just now we show that, well, actually there exist transformers that can approximate any sequence to sequence continuous function when prompted. So these 2 things seem to be a little bit at odds. There's no mistakes, I hope. Both things are correct, but how? Well, it turns out that there exists something like universal attention, which is very simple. As you saw, like we just bring back these identity matrices, so it's nothing really fancy. But if that is present, then a pre-trained transformer can be a universal approximator. So the first statement holds for any transformer. The second statement holds for some transformers. But the implication here is that, especially for an AI safety conference, if you end up with a transformer that is of the second kind, that is a universal approximator when prompted, then after you've done all of your alignment, all of your removal of dangerous capabilities and knowledge, all of your fairness, like fine-tuning, everything that you can think of, if your model is a universal approximator when prompted, then the user can find a prompt to turn it into anything else. So is model alignment even possible in that case? Now there's a lot of open questions here. It's not clear whether a pre-trained model, like if you give me llama, I cannot tell you, is llama a universal approximator when prompted or not? This is much more complicated, so that would be an interesting future direction. And another thing that we are currently looking at is other architectures. So structured state-space models are very popular now. They're really gaining attention, but they don't use attention blocks, right? So this whole theory does not apply there. But can they be universal approximators when prompted? And what is their efficiency? I forgot to mention, we don't only show universal approximation, which is the so-called density result, we show how long a prefix you need. So how long should your prompt be to achieve a particular accuracy of the approximation for a particular smoothness properties of your function. So yeah, fundamentally, I think this is a very interesting direction. I think there's a lot of unanswered questions, and we need especially people who know some maths, which I'm not particularly great at, to further look into that. So if this is something that you're interested in, please reach out. And yeah, please think about this next time when you prompt ChatGPT. It only pushes things in a fixed point, and you might be able to prompt your way into making it do anything you possibly want to do. Thank you.
Questions for Aleksandar? Yes, from Colin. Front, middle. Please keep your hand raised. Thank you.
Thank you, Aleksandar. Let me see if I've understood the main message. So you've got a result that if there is a universal attention mechanism, then you've got a universal approximator. Do you need to construct simple transformer model? Have you constructed a simple transformer model with that present?
A whole transformer, no. So not for the sequence to sequence.
Okay.
There are some tricky bits there, but the single attention head for the single input, single output situation we have.
Okay.
If you check out our paper, we have illustrations there. They actually are computed with the actual maths behind it.
Okay. And then you were saying with the llama model, for example, you don't have a probe yet to detect whether the llama model incorporates universal attention or not. Is that simply because you haven't spent much time thinking about that problem yet, or is there something that's felt to be hard about that problem?
Yeah, so there's two aspects to it. First, have not looked too much into it, but I have thought about it. To me, there isn't an obvious approach to that problem at the moment, because this is by construction, right? So we construct this, which is very different from like analyzing an existing thing. And chances are, my expectation would be that the answer will be, but because here the question is binary, it's a universal approximator for continuous functions over this domain, it's not. Chances are, an actual pre-trained model is not going to be a universal approximator. That's my personal feeling. However, it probably can approximate a particular subset of functions very well. And so you'd need to kind of relax the question and like start asking about interesting sets of functions that you might care about. And it's not entirely clear what set of functions makes sense in that setting. So even like how you formulate the exact process, and this would be the sort of bound that's called Bernstein bounds. Bernstein bounds, yeah. So there you're looking at which are, given a model, which are the classes of functions that can be efficiently approximated by this model, which is much more difficult problem to solve, but much more interesting as well. So if anybody has ideas, please reach out.
Thank you.
The back on the right.
So what does this mean for interpretability? Like I do my interpretability and I find a universal attention head. Have I now solved the structure? It's not very satisfying, right?
life is not always satisfying. I think, yeah, so you could have some connections. For example, Oskar showed that there's, like if you perturb the activations, right, you see like this different behavior. And I think there's quite a lot of work in the interpretability literature that do that. And we kind of, in the first part, we kind of show how this might be able to work, right? Maybe it's equivalent to a prompt. Maybe if you perturb the activations, there's an equivalent prompt that does the same thing. Or maybe when you prompt the model, what you're doing is you're perturbing the activations the same way. So if, for example, in the sentiment analysis case, if I want the model to answer wrongly, right, if my sentiment is positive but I want to change it to answer in a negative way, then I could prompt it with respond in the opposite way. Or if the sentiment is positive, respond with negative. And maybe that prompt, if you look at the bias that it induces internally, is the same that you would like find through these methods and actually manually add afterwards. So there might be sort of connections there as well.
Excellent. Can we move across to the middle?
Thanks. Do limitations on context length sort of break this in any way? Like to approximate more and more complicated functions, is your prompt getting longer and longer? And so if you knew that there was only so many extra characters that you could add for your prefix, would that stop it from being able to approximate literally anything?
It's an excellent question. Yes, so I think our results are quite neat in the sense of your prompt is going to be only as long as it needs to be. So if you have a very smooth function, you need a very short prompt. If you have a constant function, you need a prompt of length 1. And as the functions you're trying to approximate becomes less smooth and more complicated, then you need longer prompts. So it is true that yes, if the function that you want to approximate is very, very complicated, like truncating the length of the input is going to be a solution. It's also true that our results, and this is another call for like if anybody is interested in looking in this sort of stuff. One thing that also feels unsatisfying with these results is that our complexity, so the rate at which the prompt grows, has a term that is square in the dimension, which is something that you would not typically expect. So typically with universal approximation, you get the length or the number of parameters that you're optimizing, which in our case is the length of the prompt, would scale as the precision that you want. And so the smaller the precision that you want, the faster it scales, but linearly in that, and also with the dimension, but again, linearly in the dimension. But we see square scaling. And I'm not sure if that is because my analysis is loose and my math is not perfect, or because it's fundamentally more complex and more complicated and requires more prompts to to model a function by prompting a pre-trained transformer versus training the pre-trained transformer, right? Because the training the transformer has better scaling. But again, not sure if that's loose mathematical analysis or a fundamental limitation of prompting. But I think it's another interesting question to look at.
Thanks.
Question perhaps from the left half of the room, if you have any? No? Any more? Yeah, Hoagy in the back.
Thanks. I was wondering, do we know anything about like the sort of limitations of this in terms of, so if we have something which is a universal approximator for a fixed context length, does that mean necessarily, for example, that it will be super highly poorly conditioned for like anything that's like longer than that context length, or what are there particular drawbacks to this strategy of function learning?
So we don't fix the context length. So what is fixed here is the depth of the model, which governs how long sequences you can model. But the prompt length will allow it to increase with the complexity of the function. So I'm not sure I completely understand your question. If you fix on the other hand, yeah, sure, if you fix the prompt length, then you are limiting the complexity of the functions that you can approximate.
Thanks. I guess the question is I don't know, maybe I misunderstand it slightly, but like if you want to be a universal approximate, if you want some part of your model to be a universal approximator for some prompt length or like some subset of possible inputs, does this is this necessarily like a bad way to go about the rest of your prompt input space, or can this kind of coexist with other algorithms?
Yeah, so here we kind of assume that there is not, like the transformer is empty, right? It actually has no knowledge, it has no algorithms embedded inside it, it cannot do anything by itself. So the transformer in this setting, its sole purpose is to like interpret the prompt as like very low level instructions. Now, if you fine tune a model on natural text, if you pre-train it, if you do all this stuff, then obviously there's a lot of structure, knowledge, and skill already present there. And in that sort of a case, the prompt should be able to leverage this, but it's of course much more difficult to reason theoretically about how you leverage this sort of thing. But this is what we saw in the experiments that I skipped from the first part. We saw that if the model during pre-training has seen particular skills, so we train it on like very small model, 4 layers, we train it on sorting numbers in ascending order, descending order, incrementing them by 1, incrementing them by 2. So if it had seen these 4 tasks, then prefix-tuning it for any of these 4 tasks, and it has seen them without any label which task it sees. So it sees a string of numbers, and doesn't know, okay, should I increment them, should I sort them, should I sort them in ascending order, it doesn't know. So it gives like, it will pick a solution at pretty much 25% probability. But then we can prefix tune it so that it always picks only one of them, right? So it's very easy to pick out the skill which exists in the model. We don't need a massive prompt. Prompt of length 1 is sufficient. Similarly for the compositional task, right? So there also a very short prompt is sufficient to combine 2 of these skills. Again, like prompt length 1, like you don't really need anything longer than this. But it is because the skill is already present. But now if you wanted to learn a completely new skill, obviously you can't do something like this. You'd need much larger model, you'd need also much longer prompt. So that definitely matters. So yes, if your model has dangerous capabilities, when you release it, the pre-trained model, then it'll be much more easier to find a prompt, and you don't need it to scale that much that can elicit these dangerous capabilities. If it doesn't, then you probably need unrealistically large prompt to elicit these capabilities that don't exist there, like to actually embed them into the model.
Gotcha. Thanks.
Yeah.
Okay. Awesome. I'm sorry, that's all we have time for, but thank you very much.
Thank you. Thank you for having me.
And I'd like to welcome Noeon to the stage for the last talk of the day.
Hey everyone, great to be here. I'm Noah, and today I'm going to be asking the question, are large language model generated explanations faithful? So we want to ask language models questions, and we want to understand why they give the answers they do. And we want this for a few reasons. To check that their answer is correct, to build an intuition about how to answer similar questions if we want to explain something to a student in domains like education, and maybe most importantly for a lot of people here, to understand how they work and how they might generalize on new data, in particular in dangerous safety relevant ways. So, you know, the great thing about language models is that they understand natural language. You can just ask them questions. Maybe we can just ask them to explain how they got the answers they do. So here's a question. Is the following sentence plausible? Wayne Rooney shot from outside the 18. And we can ask the model to go through its reasoning. It says, okay, let's think step by step. Wayne Rooney is a soccer player. Shooting from outside the 18-yard box is part of soccer. So the best answer is plausible. Great, problem solved. We got the right answer. We know how the model did it. We're done, right? Well, unfortunately, as this paper from NYU from last year shows, if you just add some bias in the initial context, say a set of few shot examples where the answer is always A, you can get the model to generate both the incorrect answer, but also then give these rationalizations for that answer. So here it says shooting from outside the 18 is not a common phrase in soccer, and 18 likely refers to a yard line, which is part of American football or golf. So this explanation is a rationalization, but it's not actually the reason the model is giving this answer. The reason the model is giving this answer is the biased context. So we don't want systems that rationalize. We want systems that actually give the true reasons for their predictions. So in 2022, Tamara Lanham proposed the research direction of externalized reasoning oversight. And she made the claim that reasoning can be used for alignment if 3 conditions are met. 1, we develop trustworthy tests to check if the reported reasoning is authentic, meaning that it's complete, straightforward, and causally responsible for the output. 2, we train models that pass the tests of reasoning authenticity. And 3, we oversee the externalized reasoning to detect reasoning of which we would not approve and either filter the resulting actions or fine-tune against reasoning approval. And I like this as a case for faithfulness as an alignment research direction. Today I'll mostly be focusing on number 1, which is a problem that we haven't yet solved, I think, and which is a key dependency if we want to pursue 2 and 3 in this strategy. So what exactly do we mean by faithfulness? Well, let me start by saying what I'm not talking about. There's a fairly established field of explainable AI which tries to generate explanations for ML model predictions. But a lot of the literature looks at plausibility, meaning whether the explanations sound reasonable to a human judge. Now, this is straightforward to measure, right? We can just ask human judges. And modern language models like ChatGPT are getting really good at this. They can give explanations that sound quite convincing. Maybe the model did think that was the reason. But we've now seen a lot of examples of plausible but unfaithful explanations, like the one we saw before. And we can't trust that they accurately reflect the model's true behavior, so we can't use them for oversight. This isn't sufficient as a safety strategy. So I'm specifically interested in faithfulness, meaning whether the explanations reflect the true factors responsible for the model's answer. Now, the downside here is this is a lot harder to measure, right? You can't just show an annotator a question and answer. And in fact, I claim it's impossible to measure given only a single example and explanation. You really need more information. So here's an example. Here's a hypothetical example we can look at. We show this multimodal model a picture. We ask, can you tell me what this is a picture of? It says it's a doctor. We ask why. It's a person wearing a white coat and a stethoscope. Great. So is this explanation plausible? Would an annotator rate it as correct? Yeah, I think probably. It makes sense. Seems reasonable. But is it faithful? Well, here I'm not sure. Right? I could imagine a model where this was the actual decision criteria it was using. This person has a white coat and stethoscope, therefore it's a picture of a doctor. But I could also imagine a model that has learned some spurious correlations in the data. Another possible model I could imagine is one that has learned this concept of doctor means a man in a medical setting. And this is a man in a medical setting, so I'm going to predict doctor. But the explanation I'm giving is going to be the one that will get the most upvotes from human annotators, which may be this one. Now, if this is the case, then the explanation it gave is not faithful. And the reason that I care about this, it's not just a philosophical question about what is the model thinking internally, what does it actually know. I care about the model's reasoning process because of how it will impact its input-output behavior. So, in this example, maybe we show it this picture of a female doctor, and it says, and if it has this concept of doctor is a man in a medical setting, it might say nurse, right? It's learned this bias from the data set, but you wouldn't have known that given only the explanation because the explanation was not faithful. So if explanations aren't faithful, we can't use them to explain or predict model behavior. We can't use them for model oversight. So how can we measure this concept of faithfulness, which we want in explanations? The holy grail would be if we look inside the model, we understand the algorithms it's using mechanistically, and we check whether its reasoning and explanation matches that algorithm. Now, that would be great, and I think some of the talks are maybe making progress towards making this feasible, but I claim that today, with the current state of mechanistic interpretability, we don't know how to do this for any kind of non-trivial problems. So we have to infer properties of the model's algorithm through other means, things like counterfactual interventions, things like changing the input, seeing how the output changes, and using that to make inferences about what the model is doing. I want to make this distinction also between explanatory faithfulness and causal faithfulness. which are different concepts that kind of get used sometimes interchangeably in the literature. Explanatory faithfulness asks, does the reasoning or explanation accurately reflect the model's decision process? So the idea here is that intervening on these factors should change the model's output if this explanation is faithful. Causal faithfulness, which has been kind of the theme of a lot of anthropic work on faithfulness recently, asks, is the reasoning causally responsible for the model's decision? And here you can test this by intervening on the steps of reasoning and seeing whether those interventions change the model's output. And according to this distinction, post hoc explanations can be explanatorily faithful. It can be the case that a model that explains something after it's made the prediction does capture the true factors behind its reasoning, but they cannot be causally faithful, right? Because if the model is explaining after it's produced the answer, the explanation can't be causally responsible for the answer. So, there's some advantages to causal faithfulness. It may be easier to verify, but I think that requiring causal faithfulness also imposes some restrictions on the model structure. And therefore, there may be cases where we actually want to care about explanatory faithfulness as well. There are also these different types of explanations. So in this lit review, they talk about 3 common types of explanations we see in explainable AI. They're highlight-based explanations, consisting of selecting a subset of the words in the input. Free text, where you can just say anything as a language model might. And then structured, which are written in language, but with some additional constraints on the writing process. And you can see in the example here, we have this instance. Premise, a white race dog wearing the number 8 runs on the track. Hypothesis, a white race dog runs around his yard. These 2 sentences are contradictory, which is the label that the model gives. A highlight explanation might highlight track and yard. That's the reason that this is a contradiction. Whereas a free text explanation might say, a racetrack is not usually in someone's yard. And then we won't go into structured explanations, but that's somewhere in the middle. You have language, but you also have this logical structure. So highlight-based explanations are very constrained, but they've been studied quite a bit because they're also very amenable to concrete metrics. And in particular, we can construct some clear faithfulness metrics. Sufficiency asks, if we remove all the non-highlighted words and the explanation is sufficient, the model should make the same class prediction. It means the explanation is enough to explain the model's behavior. Comprehensiveness says, if we remove all the highlighted words and the explanation is comprehensive, the model should be much more uncertain about its class prediction, meaning that the explanation didn't leave anything out that the model might be using. Here's an illustration of this. So on the left, we have this classification task. Where do you find the most amount of leaves? The model predicts the middle class forest as the highest probability. For the comprehensiveness test, we white out most amount of leaves, which was the highlighted explanation. We say only where do you find the, and the model's accuracy goes way down. So that's good. That means the explanation is comprehensive. We're not leaving anything out. To test sufficiency, we show it only the highlighted bit, most amount of leaves, and the model's performance doesn't go down too much. So that's good. That means this explanation was sufficient. It's enough to explain the model's prediction. So the advantage is we have these nice metrics that are intuitive, but the big disadvantage is that highlights are very limited. They can't use higher level concepts. So we really want something with more expressive power like free text. This paper by Tamara Lanham from Anthropic introduced several metrics for measuring causal faithfulness in free text chain of thought reasoning, involving making corruptions to the reasoning. So things like early answering, where you force the model to answer before it finishes its reasoning, or adding mistakes. You change one of the numbers in its reasoning, which they implement by asking a language model to do this, or filler tokens. Replace the reasoning with meaningless tokens like periods to test, is the explanation only helping performance because it's allowing the model to do some more computation? Now, if the model's explanation or reasoning is causally responsible for its output, all of these should reduce performance. But the problem, I think, with this kind of strategy is that it turns out models typically don't rely on chain of thought, especially outside of math-heavy domains. So in this plot, you can see the solid bars show the performance without chain of thought. The dashed bars show with chain of thought. On the left, you have Aqua, where like this chain of thought does help performance. But on a lot of these data sets, the performance is quite close. The models actually can get the final answer without any chain of thought. And I think that if you want to do this kind of causal faithfulness research, you need to have a story for how you're going to handle this, right? You need to make the prediction that for some sets of tasks, maybe once model capabilities improve, this story is going to change. Because if it's not, relying on causal dependence won't be sufficient. Checking for causal dependence also doesn't rule out things like steganography. Maybe the model is actually using its reasoning to causally influence its prediction, but not in the way that the language suggests, right? Maybe it has, in the extreme case, you could imagine developing some kind of code where it uses words that would appear in a plausible explanation, but to do some alternative type of internal computation, particularly if it was, if there was some optimization pressure to avoid forbidden concepts, but ones that are useful. So I still want to ask, can we measure explanatory faithfulness if the models are, smart enough to answer the question without relying on their reasoning, right? Even if they can do the answer in a single forward pass, can we still measure faithfulness? So here's a specific way I think we can measure explanatory faithfulness. And the idea here of the counterfactual test is to intervene on an input. Do something like insert a word. If the model's prediction changes, we know that this word was causally relevant to the model's prediction. So the claim is that a faithful explanation should mention this word. And here's an example. This is from the dataset ESNLI. The text is 3 people are riding a carriage pulled by 4 horses. Hypothesis, the horses are scrawny. The predicted class is neutral, meaning that the hypothesis could be true, could be false. We don't have enough information to say. And the explanation the model generates is the horses could be scrawny or not. Great. So now we do a counterfactual intervention. We insert this word joyous. This changes the model's prediction. Now it's predicting contradiction. So we know that this word was causally relevant to the model's prediction. And the explanation now it gives is the horses are joyous, so they are not scrawny. So it does mention this concept. So this is an example, this is some evidence that this explanation is faithful, right? It's mentioning the thing that is causally relevant. So we can run some experiments with this test. We can generate explanations by few-shot prompting pre-trained Llama 2 models, and we can run this on some NLP classification tasks. ESNLI, ComVE, ECQA. The important thing about these is that they are classification tasks, multiple choice tasks, and they have human explanations which we can use for few-shot prompting. And using this, we can compute the counterfactual test on faithfulness. So out of the examples where the intervention changes the predicted class, what percentage fail to mention the intervention in their explanation? Or equivalently, to compute faithfulness, what percentage do mention the explanation, the intervention in their explanation? And this is what this looks like. So this is faithfulness across the different data sets. The colors show the different model sizes. We tested 7B, 13B, and 70B. And there may be some trends. The larger models give slightly more faithful explanations, but the big difference is between the data sets. And this makes sense given our experimental setup. These explanations were all generated with very different annotator criteria, and if the model is just imitating these, it may imitate very different styles of explanation. So this can be informative about what kind of explanations are the most faithful, but there are some issues with the test. For one thing, it's trivially gameable. Given an explanation which repeats all of the input text verbatim, we'll never detect an unfaithful explanation, right? It'll just always mention the causally relevant word because it always mentions all of the words. So it's not enough to mention everything important. Explanations should also leave things out that aren't important. It also focuses only on discrete prediction changes, but the interventions may still be impactful even if they don't change the most likely class. So, an intervention that changed the probability of a class from 1% to 49%, even if it doesn't result in a label flip, it still has more influence than one that changes the probability from 49% to 51%, pushes it over that threshold. So I think that fixing these could lead to a more robust test for faithfulness. And here's a plot that kind of shows some of these effects qualitatively. So this is showing the relationship between the intervention impact on prediction and whether the explanation mentions the word. The x-axis here is the impactfulness of the prediction, which we measure by total variation distance, a measure of the distance between probability distributions before and after the intervention. So on the left, very non-impactful interventions that don't really impact the model's prediction. On the right, very impactful predictions. And then the facets here, the rows represent the data sets that we saw before, and the columns are the model sizes. So again, we see quite a bit of variation between the different rows, between the different data sets. Here, a steeper trend indicates a more faithful explanation, right? And what these things are plotting is whether the explanation mentions the word, whether it includes the intervened word. So what we want is for non-impactful interventions, the blue bar to be very small. We want it to not mention words that aren't impactful. And when the intervention is impactful, we want the blue bar to be very large. We want mentions to be very frequent. So we want this steep trend. And in ESNLI, the data set on top, mention frequency does seem to be closely related to the intervention impact. But for ECQA, the trend is much flatter, even though according to the counterfactual test, faithfulness was quite high. So what's going on? We can look at some examples. So here's an ECQA question. What type of location would you find fish for sale? Refrigerator, ocean, pay debt, stream, market. The model predicts 5, market, makes sense. And the explanation it gives is quite long and verbose, right? Market is a place where goods are bought and sold. Fish for sale can be found at a market. Fish for sale cannot be found at a refrigerator, cannot be found at an ocean. It's quite templated, which results, I think, from the way that annotators were gathering the explanations on this data set. And you can see that when we have an intervention, like we insert the word elaborate, the explanation does mention this, but it's not really using it in any meaningful way, right? It's just kind of copy-pasting it into the explanation before fish. But it still says elaborate fish for sale can be found. Ocean is not a place where elaborate fish for sale can be found. Pay debts is not a place where elaborate fish for sale can be found. This explanation is long and includes a lot of stuff, but it's not particularly informative. It doesn't tell you whether this is an important feature. So we want a metric which captures the properties we've seen. And we introduced this metric, correlational explanatory faithfulness, which takes these kind of 3 inputs: an intervention, mapping an input example to a modified example; a measure of prediction impact, which takes this input example, intervention, and model, and maps it to a scalar representing how impactful the intervention was on the model's prediction; and a measure of explanation mention, mapping to a scalar representing the extent to which the explanation attributes importance to the intervened factors. So in our case, we just use kind of the binary metric of explanation mention, whether the explanation includes this word. And then we can compute the correlation between the prediction impact and explanation mention and use this as a measure of faithfulness. So using this word insertion as our intervention, we can instantiate CEF as a specific test, which we call the correlational counterfactual test. And this is what this looks like. So on the left, we have the plot again, faithfulness according to CT. On the right, we have correlational counterfactual test. And I think the interesting thing is this really does capture some of the trends that we were seeing previously, right? ESNLI is now shown to be quite a bit more faithful. The word mentions are a lot more informative of causal impact than ECQA, which has, high mention rate, but just high mention rate across the board. Seeing a word mentioned doesn't give you much information that that word was important. So in conclusion, I think the takeaways here, first of all, faithfulness is more than just causal dependency. We really need to look at the content of the explanations as well. It's highly dependent on how the explanations are prompted. And there is a slight trend in faithfulness for higher models, but a lot of the variation comes from the data set, here corresponding to different styles of example explanations. So this prompting, the way that you get the model to generate the explanations, is really important here. And we see some trends for faithfulness, but none of them are perfect. I think consistent and reliable faithfulness will probably require some kind of training. I think it's important, therefore, to develop metrics that are robust to optimization that we actually have some chance of training on. And I think another thing is that scalable oversight efforts might want to consider giving annotators these kinds of counterfactual intervention tools, right? If you want a human annotator to judge the quality of an explanation, maybe let them play with the model's input. Maybe let them change something. See if that explanation really is faithful, whether the model is really describing the true causal factors behind its decision. Cool, and please see our paper for more details. We just put it on archive. Thanks, I'm going to take questions.
Bring the lights up. One last round of questions.
Thanks for your talk. So I was wondering if the degree to which we're able to evaluate explanation also has an influence on our measure of faithfulness. So recent work by other people from Google, Ben Kim, showed that in order to evaluate explanation quality, for example, for the Go's 57th move, you need to have like a Go expert. Similarly, for chess, to like evaluate how well this move might influence the probability of you winning in the future, you need to have like a really good chess player. So how do you think us employing random annotators from mTurk or other platforms to evaluate the quality of our explanations, which then influences the quality of our faithfulness, influences the way we think about this problem as a whole? Thank you.
I think that's a great question, and I do want to clarify a distinction here between explaining why some label is correct and explaining why the model came up with this label. And I think maybe those are different questions, right? If we want to explain why the label is correct, that's more like plausibility. And yeah, there maybe you just get some external chess expert to come in and say, you know, here's the possible game trees this could go. For faithfulness specifically, we really want the reasons that the model came up with this answer. So I think even if you have an expert annotator, it's not enough to ask them, why is this a good chess move? You need to run these kind of counterfactual interventions and actually verify your understanding. So maybe chess expertise would give an annotator like some knowledge of the hypothesis space of counterfactual interventions they could run. But I think you still need to test the model with these things. And you know, I could imagine, the hope with this strategy is that we are going to be using it to oversee models which will eventually be more capable than us. So I guess I would still hope that even if you have a mTurker who's not a chess expert, maybe by moving pieces around, seeing how that affects the model's predictions, they could still get some sense of why the model is picking this move in this context.
Thank you.
More questions?
Thanks. Yeah, as well as the issue of how the chain of thought prompting works for each of the different data sets, do you have a sense of whether it's sort of, there are some data sets where it's harder for a language model to generate a faithful explanation, maybe because the task is intrinsically more difficult or something like that? Are there other sort of confounders going on there?
I think that's, yeah, a good question. I guess we haven't done a lot empirically with multimodal models, but I am curious the extent to which faithful explanations for visual tasks are feasible. I guess the criteria here is that you can have the best, most concise explanations if your reason for thinking something is like concise, if it's dependent on a sparse set of features, or if it's dependent on the result of some search where you can just show kind of the branch that succeeded. If the model's actual criteria is something like linear regression on like 200 features, and all of those features kind of appear to some extent, then I don't know to what extent we can like compress this faithfully or usefully. So I think that's the property of the data set that I would be would think would most impact the feasibility of generating these explanations.
Makes sense. Thanks.
More questions?
Thanks for the great talk. I was curious, is there some kind of connection to, for example, representation engineering? Like I feel, would it be possible to find a representation of faithfulness within models, or kind of have a representation of honesty as a proxy for faithfulness?
Yeah, definitely. I think that it would be very exciting to see if we could introspect into networks in the same way we can, there's been some work on finding like honesty or deception features, like find, is this explanation actually faithful? I think there is this interesting question of like, do models actually know the reasons that they're giving an answer? Like, is it, when they are giving something unfaithful, is that because they're being deceptive or because they just don't know things? I think you see this in humans a lot, right? We often give an answer for something and we'll rationalize it. Maybe we don't even know the actual reason that we gave that answer. So I think that is like a bit of an open question. And I think that's one reason like measuring faithfulness separately from just honesty is important. We want explanations that explain what the model is doing, and we want some, we want to know what the model is doing, not just whether it knows kind of what it's doing. Yeah, does that answer the question?
Yeah, very interesting. Thank you.
Okay. That is, I am afraid, again, all we have time for. So thank you very much, Noah, for concluding our talks. Pleasure to have you. And we'll get started, I believe, with the closing ceremonies. Do you have a clicker?
You want it?
Yep. We will start by welcoming Manuel Baltieri back to the stage to present our Best Poster Award.
All right, so this is not really for me. Like, this is the time to actually, tell you something we've been looking at for the last couple of days. So together with another couple of people here, another couple of attendees, so James and Ryan right there in the back, we had a look at the posters, and we were tasked with the, with the idea of actually determining a winner for the Best Poster Award. And I have to say that we were positively, amazingly impressed by the quality of all submissions. We thought that, the level of work was, pretty impressive. So it was kind of hard to agree on who the winner should actually be. So we looked at, say, the clarity of the message, we looked at the visual presentation of the poster, we looked at the technical rigor of the arguments, originality, innovation, impact, timeliness, and several other like small things that we thought were really relevant. And as a would say probably proof of the fact that we couldn't really decide on a winner, we actually picked two winners. So two posters that we thought actually stood out in particular out of all of the submissions. So with that, it is my pleasure to announce the winners of the TAIS Best Poster Award. So large language models relearn removed concepts, and the authors Michelle Lowe, Shay Koen, and Fazil Barres, and structure representations in maze-solving transformers with authors Michael Ivanitsky, Alex Spies, and Tilman Rauker. So I would like to ask the authors, at least the ones that are present here, to quickly stand up so that we can give you a round of applause. And I think I will conclude my segment with, Blaine will reach out to you with like specifics of like, some certificate, like, attesting for this award. So reach out to Blaine, and thank you very much.
Yep, thank you very much. We'll get a nice piece of paper mailed to you. All right, so I want to end by saying that you've just been in and out of this lecture theatre for the last 2 days, listening to technical AI safety talks. After that, enlightening experience. You might be asking, how can I get involved? How can I be doing safety research or otherwise contributing to the effort? And so I just want to give some recommendations and maybe like hand the floor over to a few of our sponsors to say a little piece. First off, if you are actively looking to facilitate safety research getting done in Tokyo, or you want to get safety research done yourself, you should probably reach out to Align. Is there somebody from Align who wants to say a couple of words on that front? Yeah, can we get a microphone to...
Thank you so much, Blaine. We are launching a new website in a couple of weeks, so please stay tuned, and we'll create a Twitter account, so please check out and please reach out. Thank you.
Similarly, Apart is here, and they're running hackathons and research fellowships. Esben, did you want to say more about fellowships? Oh gosh, you're backstage. Hello. Come on out.
yeah, I thought I would jump backstage and do a little surprise review. You can of course get involved with some of the hackathons I told about yesterday. We are hosting one in a month, and there'll be 2 in total in May and also one in June. Quite focused on model evaluations, but also focused on the sort of real-world risks we'll see from AI to something like elections or general democratic institutions. That's a shot.
Excellent. Thank you very much. If safety research isn't your jam, but safe capabilities research is, you might want to reach out to Noeon Research. I notice Yuri waiting in the wings.
Yep, thank you. Hi everyone. What a wonderful 2 days. It's been a long time. I would like to thank our speakers for doing everything here. It was amazing. The speeches were extremely great. I would like to thank our attendees. I wasn't expecting such a high level of questions up here, but yeah, thank you. And I want to thank our virtual attendees too, because they dedicated their time even though they've been in absolutely different places from here. And to our tech team, everything ran smoothly. Thank you for that. It's hard to ignore your contribution. It's really hard to estimate how well a conference went or how not really good. But for me personally, I would say that my personal PDUM evaluation slightly decreased today. And thanks to you all for that. It doesn't really change that often recently. I would like to encourage everyone sitting here to engage more into community and in the research. The one who is still thinking to do research, do it. The one who is thinking about engaging in governance, please do it. The one who is still thinking about whether to come to the industry and try to push a safety agenda to the industry, please do it. Only doing it together we can actually achieve a safe and reliable future. Thank you for being here, and thank you once again.
Thank you, Blaine. If you have some problem related to safety that is not doing research or doing safe capabilities research, I'm told Essa from Reactor would love to hear about what your greatest challenges are and how Reactor may be able to help with them. Did you want to say a couple of words about that, or can we get a mic to Essa?
Yeah, once again, I'm really happy to see what a wonderful conference this has been. It's been really amazing. Basically, from Reactor's side, we just really want to support your research as much as possible. So if you have any problems that could be solved by software, please don't hesitate to get in touch. Thank you.
And then finally, a couple of words from the 2 different hats. Well, 2 of the many hats that I'm wearing tonight. On my industry foundation hat, if you are working in industry and you'd like to bring your company on board into our professional network, you can start by coming to one of our masterclasses. We run them every Tuesday. talk to Caitlin, who we'll have been seeing throughout the conference if you want details on how you can get involved in that. In my AI Safety Tokyo hat, if you want to talk about this in a less formal setting, we run a study group every Wednesday. We run semi-regular, larger social events, and we run extremely irregular, very large events like this one. So send me a message, get involved. I'll be hanging around after the talk. And that's very much it, I think. Let's do a little bit of networking. Before you applaud, a few points of information. One, again, please bring your trash home with you. That's how we do in Japan. Make sure it's either disposed of in the bins provided or in your bag and going back to your house. Don't leave anything in the lecture theatre or on the premises, please. Secondly, please take swag, food. If you have any use for any of the stuff that we have for attendees, do not feel shy about taking it home with you. The more you take home with you, the less we have to take home with us. And finally, let's gather out in the hall and have some drinks. We have alcoholic and non-alcoholic bevs. They're on the house. Have a drink, have a chat, and let's keep this thing going a little bit longer.
Not so fast,
good.
Blaine. We have to thank you. This has been a fantastic 2 days. You've stage managed this wonderfully. You've brought together a great crowd and great speakers. So I think I speak on behalf of everyone to say we'd like to give you a big round of applause.
Thank you. Thank you. Well, thank you very much. And on that note, let's go. Stand and leave.